guess that courage ain't allowed. Evidently you're not in the mood, and everything I say just bothers you. You built this fortress, I stumbled towards it. Evidently you look furious, walls up and I know you're serious. Evidently I'm not always there, but you left and I looked everywhere. You built this fortress, I stumbled towards it, I stumbled towards it. And guilty I may be, but don't give up on me. In the wake of the odyssey, we will still be thick as thieves. You and me still thick as thieves. Evidently this is my mistake. Lost touch but I think I've been replaced. Evidently something's gotta give. Play it safe but I know you're worth the risk. You built this fortress, I stumbled towards it, I stumbled towards it. And guilty I may be, but don't give up on me. In the wake of the odyssey, we will still be thick as thieves. You and me still thick as thieves. I got an escape if you want it. We can leave first thing in the morning. We'll be back before you know it. We're as big as thieves. And guilty I may be, but don't give up on me. In the wake of the odyssey, we will still be thick as thieves. And guilty I may be, but don't give up on me. Don't you give up in the wake of Evidently we can't work it out. I guess that courage ain't allowed. Evidently you're not in the mood, and everything I say just bothers you. You built this fortress, I stumbled towards it. Evidently you look furious, walls up and I know you're serious. Evidently I'm not always there, but you left and I looked everywhere. You built this fortress, I stumbled towards it, I stumbled towards it. And guilty I may be, but don't give up on me. In the wake of the odyssey, we will still be thick as thieves. You and me still thick as thieves. Evidently this is my mistake. Lost touch but I think I've been replaced. Evidently something's gotta give. Play it safe but I know you're worth the risk. You built this fortress, I stumbled towards it, I stumbled towards it. was wondering if after all these years you'd like me to go over and
Good, and good. So I'm very happy to be here for the third time in Panama. So I would first of all like to thank, no, David was here, so now it's David, but I would like to thank David and his team, and I would thank Jim for moderating this session. I'm really happy to be here again in Panama. And yeah, we enjoyed a very nice lunch, so I hope that the lunch was not too good and you can still stay awake. And I also heard that I should talk a bit slower to give time for the translators. I will try to slow down. So my talk will be about far-red light. We've heard already a little bit about it this morning. So far-red light, yeah, I could say it is very dark red light, but we hardly see it by our human eye. Usually it is not considered to be relevant for the photosynthesis of the plants. We can debate about that, but it has a lot of effects on the plants. So that's where I want to focus on. But before doing so, I would like to look a little bit on growing crops in greenhouses, in vertical farms, and maybe it's nice to look a little bit back in time. These were pictures, let's say 100 years ago in the Netherlands, low technology level of producing crops. Then this was probably mid of the 20th century. We see already a little bit more technology, but compared to now, it's not so much. This is what we might call a modern greenhouse, made of glass. We see already the lamps, the high-pressure sodium lamps, much more technology. But where I say modern, well, to be honest, this picture was taken in the year 2000, so that's almost 20 years ago. And technology is further progressing. We have now LEDs. Those LEDs also, we will see them more and more in greenhouses. They also make vertical farming possible. What is vertical farming for me? It is, if we look back in history, a logic next step on controlling the production process. We don't need much area now anymore to produce a crop. Yesterday someone asked me, how much less land do we need? Well, that's hard to say. What do you exactly compare? Usually I say, well, in a vertical farm, on one layer, we can produce the same as in a greenhouse. If we look, well, then where is the greenhouse located? If it's the greenhouse in the Netherlands, with some lights, a Dutch tomato grower produces 90 kilograms of tomato per square meter on an annual basis. Well, if you would manage to do so in a vertical farm, very much depends on how much light we install. Well, and then think about it, you have a number of layers above each other. then it's much more than in a greenhouse. And compared in the open field, yeah, probably it's not a fair comparison, but if you would grow tomato in the Netherlands outdoor, that's hardly possible, but you would not get 10 kilograms per square meter. So from less than 10, in a greenhouse maybe 90 kilograms, in a vertical farm, many layers above each other. It can be anywhere. It could also be here in Panama or wherever in the world you can grow, you can have a vertical farm. We are not dependent on the outdoor climate. It's very sustainable on many aspects. However, we should not forget the electricity use is huge at this moment, and that's what we need to bring down. And we are working on that. And very important is now we can have a very consistent quality. We can really guarantee every day of the year how much to produce of a very specified quality. There's also a disadvantage on the price. If I compare it to producing in the Netherlands in a greenhouse, which Ido in this morning indicated already, well, producing in a greenhouse in the Netherlands is relatively very cheap. Then comparing to vertical farm, the vertical farm is probably 2 to 3 times higher cost price. On other locations of the world, this difference in cost price might be very different. Okay, I started with some pictures looking back in time. This is more at present when you go in a vertical farm. And I took a few pictures in Europe. Here one example in the UK, a large farm, or container farms, what we see, this one in Paris with the strawberries, or what you see popping up in supermarkets, or even at the houses where people can buy small systems to have in their kitchen or in their living room. I would like to focus on what light is doing with the plants and how we can use that to control the crop. Well, and then we need to understand a bit more what light is doing. But what factors of the light are we looking for? First of all, how much light, so the light intensity, and that drives photosynthesis. But it is not about only about the amount of light, it's also the photoperiod. So how long is the day, how long is the night, and that affects the many developmental processes of the plant. Then it is about the color of the light, what's often indicated by the light quality or the spectral composition. The direction of the light, the solar light, comes from the top. With the lamps, we can choose. It can be on top. It can be in between the canopy. We could even choose from below. Whether it's wise or not, well, we can debate about that. And with light, usually it means there's also heat. And we should not forget that heat component. Is that good or is it bad? It very much depends on the situation, what the temperatures, because plants have optimum temperature. Well, and then if you look at what a plant, if you really want to use the light to control the growth of the plant, we need to understand what processes are involved. It's the photosynthesis, production of the sugars. It's about the morphogenesis, the form of the plant. It's about developmental aspects, the formation of plant organs, the abortion of the plant organs, the ripening. And all those processes are interlinked because the morphogenesis, the form of the plant, affects, so let's say, the shape of the leaves, the area of the leaves, the orientation of the leaves, that affects how the light is intercepted. And depending on the interception of light, we get more or less photosynthesis. Photosynthesis, as sunlight produced, affects the morphogenesis. But it was also about water relations, the transpiration, the water uptake. That affects then the opening of the stomates, the small holes through which the CO2 should enter the leaves. The cell expansion. Well, I will make it today not too complicated, but if you really want to use the light, if you want to use all the other climatic factors, I think we need a profound knowledge of how these processes affect the plant. Going back to the LEDs. Energy use is an important issue, whether we use it in a greenhouse or in a vertical farm. At this moment, in the greenhouses, the HPS, high-pressure sodium lamps, are still the standard lamps. Most of the greenhouses where they have light, it's like that. Well, and then if we look on how much light is produced per joule electricity, it is roughly about an HPS lamp produces about 1.8 micromole of light per joule of electricity. So micromoles, for those who are not familiar, yeah, that's the quantity of light that you have to look at if you want to know how much light is there. An LED Well, a modern LED probably at this moment is up to about 3 micromole per joule electricity. Some companies claim to be already a bit higher. I should also make a warning, not all LEDs are there. They're also, if you just buy an LED, I would recommend first look on how much light it produces per joule electricity, because otherwise you might get problems in the electricity use. So the LEDs, they are efficient compared to other light sources. We can now choose the spectrum. We can choose where to put the lamps. The timing is important for plants. There's hardly any heat radiation, so that's nice that we can separate the control of heat and light to a large extent. Disadvantage is the investment cost. With plants, plants that can sense the light, first the light for photosynthesis, then they have a number of receptors, so let's say pigments, which perceive some specific colors of light. And here on this scheme you will see the most well-known photoreceptors, and because today I will focus only on the far red light. Well, far red light is perceived by the pigment, by the phytochromes. Phytochromes, molecules receiving or perceiving the far red light. And with phytochromes, it's like a switch. It can absorb the far red, it can absorb the red light. And in fact, it's about the ratio. It's like a switch. If there is more red light, it's here. If there is more far red, it's there. So it's about the ratio between the two colors. To be fully clear, some other colors also play a role, but red to far red, that's the major thing which determines the phytochrome. And the phytochromes have many effects in plants. Here you see one classical example. Young tomato plants grown under red and blue LEDs, 150 micromoles in this case. And if you go from left to right, we added far red. The left-hand side, no far red. From left to right, going up to 150. You see, with more far red, more elongation of the stems, a larger leaf area. Leaves also going a bit more upright. So classical response, what you will find in most plant species. What's also very interesting is at the most right-hand side of the graph, where it says end of day, EOD, end of day lighting. To be honest, a better name would have been start of the night, start of the dark period. So at the beginning of the dark period, we turned on the far red lamps just for 15 minutes, 10 micromoles, so short duration, low intensity, and you can imagine it's only about the ratio between red to far red. So if there's no other light on, just with a small, low intensity, you completely switch the ratio. And we do that, and if we do that at the end of the day, plants are very sensitive to the far red. Think about sunset. What happens at sunset? Think about a very nice sunset. The sun is going down, it's getting darker and darker. In fact, all the light shifts to higher wavelengths from red going towards the far red. That happens in nature. And that's probably why plants are so sensitive at the end of the day for a change from red to far red. And if you compare here what happens at the end of the day, there's 15 minutes of low light intensity compared to the completely left-hand side, you see quite a difference in the plant. So here are some tools to manipulate the growth of the plants. Same experiment, a little bit later, plants a little bit bigger. We can see again, the more far red, growth was very much stimulated. I can also show the few in some graphs. What you see here is a figure, plant dry weight on the y-axis. And on the x-axis, I had indicated here the PSS, that stands for phytochrome stationary state, but I decided not to go into detail about that. More easy for you probably to read that at the left-hand side, that is where the far red was relatively high, and at the right-hand side of the graph where it was the low far red. What you can see, when there is a high fraction of far red on the left-hand side of the graph, the plants are bigger. And what you can see here, the results from two different experiments. Same experiments, but now not the total mass of the plant on the y-axis, but the leaf area. Maybe less clear, but also here what you can see, when there's a high ratio of far red, we saw in particular a stimulation of the leaf area. What does it mean? If there's more leaves formed, in particular here, with relatively young plants, a higher leaf area means we can intercept more light. If the leaves intercept more light, you get a total photosynthesis of the plant increases. And that particular is important in those young plants, because in young plants, a lot of the light falls on the floor, and that's really a pity. That's lost light. So we need to be sure to absorb, let's say, or let's try to absorb all the light. Then we get the highest efficiency. Same type of data now presented in a different way, plotted the plant dry weight on the y-axis versus the absorption of light by the plants. And then we see more or less a linear increase from the low far red to the high far red, indicating that in these young plants, the major effect of the far red light is a stimulation of the leaf area expansion. We also did do many more measurements in these type of experiments. We saw some small effects on the rate of leaf photosynthesis. Rate of leaf photosynthesis, then I mean the photosynthesis per unit leaf area. So far about vegetative tomato plants. But of course, if you're thinking about tomato, you think about fruiting plants. What about the fruiting plants? So we did do many other experiments, I should say, but here I just show one experiment with the moneymaker, an experiment for 130 days where we had a light intensity of 150 micromoles. We did do experiments with red and blue light, or we did do experiments with white LED light, and then on top of that, we added, well, no far red, or 30 or 50 micromole of far red. It was in a greenhouse, so there was a little bit of solar background light. On average, about 12% of the light came from the sun, and the remaining part was from the LEDs. Before I show the results, I would like to take you a little bit of what we often do is how we analyze the growth of the plant. And now we get maybe a bit of a complicated scheme, but I try to keep it not too complicated. A yield component analysis, that is, we look at the yield and we analyze which components are responsible for a yield increase. So we can look at the fruit dry mass, in fact, on top of that would be the fruit fresh mass. Well, if there is an increase in the fruit mass, it can be because the whole plant was growing faster, or because the plant partitioned more assimilates towards the fruits versus the leaves and the stems. Yeah, and if there is an increase in the total growth of the plant, it can be because there is the rate of photosynthesis per unit leaf area is larger, or because there was a higher leaf area index. Well, then we can go one step deeper. If it is the leaf area index, well, it can be because there are more leaves, or because those leaves are larger. Well, then we go to the other side of the graph. Dry mass partitioning, often it depends on the number of fruits on a plant. It depends on fruit formation, fruit abortion, or it can be on the sink strength of a fruit. Sink strength is how strong an organ attracts, assimilates. Then we can go also here with the fruit number one step deeper. If there are more fruits, it can be because there is more appearance of trusses, because those tomatoes are grown in trusses, or more fruits per truss. Well, in fact, in our research, this scheme can be further and further enlarged. I will not do that today because then I needed two small letters and probably I would lose the audience. Looking at some of the results. What you see here, those two experiments with the two different background lights, background light of red and blue, or background light of white light. And we see here the total fruit dry mass in grams per plant, and on the x-axis the intensity of far red light. And we see that the more far red, the more fruit yield. And these were quite big effects. Why was that? Well, that's in fact the major thing is what we can see here. We see the two graphs, the two experiments, the one with white light, the other one with red-blue, and in both experiments where we added far red. And here we see the relative partitioning of the assimilates, or the partitioning of the dry matter, among the root, the leaf, the stem, and the fruit. The fruit is indicated by the red part in these graphs. At the left-hand side, without far red, and then the next one is with far red. And you see, if there is far red added, we see a larger fraction of the dry mass partitioned in the fruit. So what do we see with far red? We get relatively more fruits, and we get less leaves. And that's, I think, one of a very interesting finding, that we can control the balance between vegetative and generative. I must say this is an experiment, relatively a short-term experiment, still 130 days. We also have done more longer-term experiments, and they all confirm this effect on the partitioning between vegetative and generative. So it's not only a way to increase it, but if you talk to the growers, they want to have tools to control the balance between vegetative and generative. So now they have, in fact, an extra tool to balance between vegetative and generative growth. Earlier I said, well, then we do these type of yield component analysis. Well, then I give you some results of that. Here we compared when we add the highest intensity of far red light to the red-blue light. So if you see here numbers plus 44%, that means that fruit dry mass was increased by 44% when we added the far red. Why was the fruit dry mass increased? Well, then we can see here, we got a small increase in the total mass of the plant, but the major thing was the fraction of the assimilates to the fruits. But we can look a little bit further in the dry mass of the plants. Well, a small, though statistically not significant, effect on the photosynthesis per unit leaf area, and some effects on the leaf area index. Now you can also see here that the effects on the leaf area index relatively, there was a positive effect, but in small plants this effect is much stronger. But this is about the fruiting plants. Yeah, so what I indicated, I probably, looking also at the time, I should not do all the details, but the major thing that I think you should, the message is the fraction to the fruits was increased. So relatively more fruit growth with far red. What I not indicated here is the fruit sink strength, the way the fruits attract the assimilates. Well, that's in fact research where we are going at this moment much more detail in our group, and this is really an important thing, that far red really affects the individual fruits on how strongly they can attract the assimilates. But we should not only look at growth, we should also look at some other aspects. And that's what we can see here. There might be some risk for botrytis. Botrytis is a big thing in many crops, also in tomato. So from the same experiment, we took some leaves, put them in the laboratory, infected them with the botrytis, because I did not want my colleagues to infect the leaves with botrytis in the greenhouse. I hope you can understand that. I don't like that, so we did do that in the laboratory. And what you see here on the y-axis is the lesion area. So the leaf in the lab infected with botrytis, and then you measure how rapidly did the botrytis develop. Well, unfortunately, with more far red, we got a bigger lesions. So that's not directly that I can say, well, in the greenhouse in practice you will get more botrytis, but we should realize that leaves under far red might be a bit more susceptible to botrytis. So that might be a drawback of far red. So some conclusions about the tomato plants. In young plants, far red, you get a strong increase in the growth rate of the whole plant, which is mainly due to a rapid expansion of the leaves and therefore intercepting more light. In the fruiting plants, well, then anyway, we have already a large leaf area, so then increasing the leaf area is not so important anymore. But there we found the interesting thing that the ratio between fruits and vegetative parts goes more towards the fruits. So from tomato, I would like to go now just very shortly to potato. You might think, well, what potato? But I thought it's nice to show example also of some other crops. With a potato, of course, then the tuber formation is an important issue. So what did they do? In a vertical farm, we grew 3 different varieties of potato, 3 different genotypes. You see here the different pictures, and we added the far red. And I see here one of the results. Well, the first cultivar, the Indigena, did not tuberize at all because the day length was not optimal for this cultivar. So but for the other 2, what you see here is so the RH or the G254, 2 of the varieties. We looked at how long did it take before the tubers were formed. So if the bar is shorter, it means it took a shorter while before the tubers were formed. And what you can see is that if there was no far red, it took a longer time before tubers were formed. So this is an indication that also the formation of tubers can be speed up by adding far red. Then from potato we go to the lettuce plants. An experiment in a vertical farm, so let's say indoor, 220 micromoles of light, in this case red and blue, and then we added far red or we had no far red. And we did do this experiment by growing plants at 3 different planting densities. Well, here you see one of the results, which in fact summarizes everything. At the left-hand side, plants which were grown under the red-blue LED without far red. At the right-hand side, with the far red light added. And you see with the far red a much bigger plant. Well, then we can also see it in some numbers. That is what we see here. On the y-axis, the total mass of the plants versus the time. 2 lines, the red that is with far red or the blue without the far red. And you see it, the 3 different graphs indicate the 3 different planting densities. In all cases, if adding the far red, you get a higher mass of the plants, so in gram per plant. Of course, as a grower, in the end, it goes mainly about gram per square meter. I fully realize that, but just to show you what the effects does do with a plant. This is the total mass. Then we looked at the different components of the growth again. Leaf area, well, with leaf area, you see a similar thing. So also here, it was mainly the leaf area expansion, which was promoted by the far red light. Well, then again, this typical yield component analysis, something similar type of analysis as with the tomato. So on the top hand, you see the above ground fresh mass, and there it says plus 42%, meaning that far red resulted in an increase in the end of 40% increase of the fresh mass compared to the situation without far red. Well, and then you can see the different components. From fresh mass, you can go down, well, it was dry mass. The dry mass is usually the basis for growth. We see on a dry mass basis, the effects were even stronger. But that was also, yeah, if you then look at the dry mass percentage, so that's the ratio between dry and fresh weight. Well, in fact, what we see here with the far red, the dry matter percentage increased. So in fact, that results in a less strong increase in the fresh mass. And the most important is what you can see here is why was this dry mass increase so strong? That was mainly due to what you see here, intercepted PPFD. PPFD is photosynthetic photon flux density, so the total light intercepted. Increased by 60%. That was mainly because there was more leaves or more leaf area was formed. Interestingly, we also see here that the dry mass production per unit intercepted light increased by about 10%. That means if the light, once it is intercepted by the leaves, it's used more efficient. Usually if you find it, and then you would expect, well, if you measure the leaf photosynthesis rate, it should also increase. Yeah, we hardly found increase in net photosynthesis rate. We still do not understand this, and at this moment we're further investigating to understand this. But so this light use efficiency, the efficiency that the intercepted light is used. And we can see here one more result summarizing for the 3 different planting densities. At each planting density, we saw that the light use efficiency increased due to the far red by somewhere between 10 and 20%. Is it the rate of leaf photosynthesis? Well, so far we did not find a strong effect on that. We're further investigating it. Has it to do with how the light is distributed within the plant? That might also be an important issue. So what can I conclude on the far red effects in lettuce? Far red light, strong increase in leaf elongation, therefore more light interception, and therefore a stronger growth. So far about far red light. Then I would like also to take the opportunity to say one more word about the light intensity and a little bit about quality, because so far it was about growth of the plants. In the end, it's also about quality. Here you see 3 different treatments, different light intensities. In fact, what were it? Well, at the left-hand side, a high light intensity, 500 micromole. At the right-hand side, a very low light intensity. So, and this was only the last week before the harvest. And then we looked at what was the quality after harvest. And here you can see how it looked like 13 days after harvest. And I hope you can see already that at the highest light intensity, the leaves were still very nice green. At the low light, when those plants which were grown at a low light intensity, well, after 13 days after harvest, they started to get brown. Then we can go a little bit later, 21 days. Well, I would say they all don't look that good anymore, but in particular at the low light intensity, well, you didn't want to come too close to those lettuces because they didn't smell anymore very nice. So a very clear effect what we see on the shelf life of lettuce by a positive effect by increasing the light intensity. Well, and then we can look on what else changed in the plant. Well, if you go from a low light to a high light intensity during the last week of the growth, we got more carbohydrates, so more sugars in the leaves. That's maybe not surprising. More light, you can get more photosynthesis, more sugars. We got more sugars in the leaves. We got more vitamin C. Well, and then we can correlate it to the shelf life, and then we see a correlation as we would expect. So it is likely that the higher light intensity, because it gave higher concentration of sugars, higher concentration of vitamins, and that's then the likely explanation for the better shelf life. So far today, I focused on lights, and I think it was also mentioned this morning, even by the lighting company, that it is not only about the lights. And I want to stress that lights are very important, but to make efficient use of the light, all the other factors need to be balanced. We also need to look at the CO2. We need to look at the temperature. And if you increase the light intensity, you also have to modify the temperature if you want to have optimal growth. But it's also about air humidity, not to forget. Quite often forgotten. It seems forgotten sometimes in vertical farming. And then you end up with problems if you forget about air humidity. It's about airflow. But it's also about the water, the nutrients. I don't have time now to go in all those topics, but I just find it important to mention them. And then I would like to draw some conclusions. The message about far red is in young plants, with far red you get a more rapid leaf elongation. In these plants, it is very important to have as soon as possible a larger leaf area to get all the light such that it does not fall on the floor. So more leaf expansion, more light interception, and therefore more growth. There can also be some effects on the rate of photosynthesis per unit leaf area. We get more elongated plants. Is that good or is it bad? Well, that very much depends on what type of plant we are growing and what type of plant we do need. But quite often, we want compact plants. So then the far red light is not so good. And also what we have to think here is more about dynamic lighting. I think in most crops, initially with far red, you have many positive effects. But if you do it for a too long while, the plant might get too stretched, and that's not the quality type of plant you would like. So you can do it up to a certain moment. Well, then in fruiting plants, so far we only showed it for tomato, is that with far red light, we can change the balance between vegetative and generative more towards the generative. So we have, as a grower, we now have an extra tool to change the balance between vegetative and generative growth. In the end, for commercial application, of course, the question is, I showed now many positive effects about the far red light. You always have to make a consideration, do I invest in far red light or would I invest in another color? So then there are more considerations which come into play. But I focus here on the aspects on what it does do with the plants. And then before I close, I would like to make some advertisement. In February, we organized again a course on lighting in greenhouses and vertical farms. We did do this now for a number of years in a row. We always got very positive evaluations, and we always like very much the interactions with the participants. If you're interested, send me an email. but don't wait too long because usually those courses are rapidly fully booked. And then I would like to thank you for your attention, and you can see a number of companies where the results that I showed were involved in some of those experiments. So thank you for your attention.
Thank you, Leo. So questions again for Dr. Marcellus. Please go ahead and write them on a piece of paper and just raise your hand and one of the students will help you. But I actually have a couple very quick questions for you, Dr. Marcellus. The first question is it true that the green spectrum is known as a canopy penetrating spectrum? Is that true?
Yes.
Okay, yes. The answer is yes, that green is canopy penetrating. Would you like to say a little bit more about that?
I could say a bit more about that. Up to a few years we heard quite often, well, green is not relevant. Well, green, of course, also does do a lot of effects. It still is photosynthetic, active, but on a single leaf it's less active than red or blue light. If you measure on a single leaf, with green light, relatively large fraction is reflected, relatively a large fraction is transmitted, so that's lost on a single leaf. That's what you see often in the measurements. But who's growing a single leaf? No one. You're growing a whole plant, and not one plant, a whole crop. So if the green light is not absorbed by this leaf, it will be absorbed by a lower leaf. And yes, green light penetrates deeper, so you can get more light down in the canopy. Is it positive to have green light? Well, I think it's hard to say at this moment. I would say you can very well grow without green light, but whether there can be positive effects, yes, there are also effects of the green light.
Thanks, Leo. The other question I have, while some of you formulate some questions, is there a difference in the nomenclature between far red and deep red?
Yes, there is. I never use the word deep red. Sorry for my companies which I work with very much. I would consider deep red is something like a commercial name of some of the companies. So many companies have different names for red. For me, deep red is just red. They use, I think, this term because deep red is the type of red we often use in horticulture compared to the red in, I'm not sure, traffic lights, I think, or something like that. I would say that is red. But deep red should not be mixed up with far red. Far red is much darker. Deep red we see very much with our human eyes. Far red we hardly see.
Leo, thank you so much. Thank you. All right. How about a hand for Dr. Leo Marcellus, please? Thank you, Leo. Dank je wel. Okay, before I forget, I want to remind you that there is another breakout session at 2:15, also in the Controlado room. That is Patricia Gier, who will be talking about food safety. I can tell you guys today that I am very lucky to be here. Last week, I got salmonella. I got food poisoning, and I almost went to the hospital. It was awful. So, for those of you that like to go to this breakout session and learn a bit about food safety, welcome to it. So thank you. We'll talk about that in a little bit, but I want to introduce the next speaker. Before I do, I'd like to do one more little plug for our two keynote speakers, Dr. Kevin Folta from the University of Florida, who will be speaking on genetics and breeding and flavors and all kinds of interesting things. The reason why Dr. Folta is here, and he's a very interesting man, I don't know if you all saw or remember Dr. Studi's a photo this morning of some dwarf wheat. When I see dwarf wheat, I think about a very famous person who was behind dwarf wheat, and that's Dr. Norman Borlaug. How many of you all are familiar with Dr. Norman Borlaug? I'll spell that, B-O-R-L-A-U-G. In 1970, he won the Nobel Peace Prize. It is thought that because he instituted dwarf wheat into a number of countries, China, India, Mexico, that he literally saved thousands, if not millions, of lives. Prior to that point, the wheat that grew would often fall over in heavy winds. So the dwarf wheat was quite a movement. So please come and see Dr. Folta tomorrow. And then, of course, Ralph Fritchie from NASA will speak more about us going to Mars, because we're going to go to Mars. If you haven't figured that out, we're going to Mars. So thank you, guys. All right, let's move on, shall we? This is it's a double Dutch treat. It's actually a triple Dutch treat because we had Edo Kolmer, then we had Dr. Marcellus, and now our next guest, also from the Netherlands, is Dr. Jan Vestra. Dr. Jan Vestra graduated from the Technical University of Delft in 1985 with a degree in mechanical engineering and earned his PhD there in 1990. In 1996, Dr. Vestra joined Priva to focus on developing water treatment equipment for greenhouses and directing research projects in universities and colleges. Today, he is Priva's Strategic Business Development Manager, researching and developing new techniques at the cutting edge of horticulture and building automation technology. Dr. Vestra is a member of the board of the Netherlands-Canada Chamber of Commerce and part of the Precision Indoor Plants Initiative by the Foundation for Food and Agricultural Research in Washington, D.C., which I was also part of with Dr. Vestra. It's a great movement. If you would please put your hands together for Dr. Jan Vestra. Thank you.
Yeah. I'll just start talking. Yeah, it works. I felt so tied up to the pulpit that's over here, and since I'm not a pastor, I want to move around a little bit more. And you can see my trousers, otherwise I put them on for nothing, just bringing my jeans. We heard a talk by Gary Sturte, and it was about technology is key to saving our lives. And I was thinking, but the same sort of technology nearly killed us in the process since the last 100 years or so. So there's always a dark side. There's a dark side, Luke, but there's also a dark side to technology, and it's key to find out, well, how can we mitigate that part and can take advantage of the good part of what's going on in terms of controls and everything else. Well, the question was, can you talk about control, environmental equipment and sensors and everything that revolves around that? And I'm not the first one, I'm jinxed, I suppose. Here we are. Here we were. This is just to test how relaxed you are in being on stage, of course. Well, I work for a company called Priva, and just some facts and figures, that's what my boss wants me to show. So we are actively worldwide. We are about with 500 people, and we design and sell hardware, software, and all types of services that are related to it. And we do that for the horticultural environment. We do that for building controls, mainly in Europe, and also into indoor growing, where we are quite active. And to support this type of technology, we have offices worldwide. So, well, to point out, my colleague from Mexico is here as well. We have an office in Mexico, in the United States, in Canada, and several in Asia and in Europe. And in order to make the world work the way we want to, we run it through dealerships. And the dealers are the people that are trained by us in organizing all the technology. So we have a worldwide partner network. Always within several hours of your breaking down of your system, somebody is around. And as I said, we do big greenhouses, like the one on the right-hand side, 97 hectares in one session with CHP, boilers, the works, but also strawberries, advanced controls, and also, well, growing cut flowers. In terms of automation, building automation, we do big buildings in the Netherlands, but also Westminster Abbey, and Marks and Spencer's. All the shops in the UK are a Priva client, where we control the climate, that the shoppers stay in longer, spend more, and make the owners of Marks and Spencer happy, because that's what they are there for. In terms of urban farming, indoor farms, we've been working with Gotham Greens for all the new facilities they're gonna put on. This rooftop farm in Brooklyn is not a Priva system yet. 80 Acres Farms, it's been already quoted by Ido this morning, We team up with them and with Ocado to make new types of indoor farming facilities. Medicinal herbs in the UK or in the US and Canada, we can grow some. There is some legislation to make that work. And on top of that, the GrowWise facility in Eindhoven by Signify is also a Priva one. So we do solutions for indoor growing, like you can see over here on the left-hand side. HVAC controls, this is in the Signify unit, irrigation, but also we don't supply LEDs, but we can control all the daylight integral, all the colors and switches and whatever you want to make it work. But in order to gain money and to have food, all the technology is nice, but technology must not be a means in itself. And therefore we think, and we think it for a long period of time already, it all starts with the plant being in the center of the controls. And just a peek of a larger greenhouse in the Netherlands, 7 hectares in one session. And we had a campaign, 2002, and I'm around long enough to know that. And I thought, well, this is the most stupid campaign I've ever seen on a car. And all those service cars had these stickers on it, the plant is king. And on the back it said, take care, I break for plants. Well, it took a lot of it had gained a lot of attention, but nobody thought what was going on. And you see in Dutch, de plant wil van alles op de hoogte zijn. So the plant wants to know it all. 2002, we thought, how can we change our controls in having it plant-based instead of technology-based and make the most of it. And gradually we are getting there, I think. So in order to make it work, to make your growing system work, the plant must be in balance. Question mark. Because if you want to induce fruiting in a plant, you must stress the plant that it starts making flowers, that it starts thinking about the genetics, about creating offspring before it dies. So you have to stress it out to make that work. But you see everything that's already passed along, what's necessary to make a plant grow. So there's the CO2, there's the light. Well, we don't have to go into that in detail, but also the temperature changes, relative humidity, and don't forget the water part, the irrigation part, which is not so much discussed today, I think. I will do that at length later on. But think about what's going on in your irrigation water, the pH, the amount of fertilizer that's available, the micronutrients like iron, copper, manganese, whatever. The temperature of the water that can either have growth induction or can hamper your growth to a big extent. And we think, and I think most of the people agree with it, to make it work, to have all these different functions work at the optimal level, and optimal is not always the best for one, but it's the best for the whole system. We need an integrated control system. And what do we have to think about integrated controls? Well, if there are more parameters to change, like in a greenhouse, let alone going into an indoor farm, a vertical farm, we have the heating, ventilation, and air conditioning. That takes care of humidity control, takes care of the temperature, but also we have light, we have irrigation, we have to take care of energy and the CO2 levels. And it's all entwined. And you saw the picture Leo showed about the growth of a plant, its light, its morphogenesis, and all the different issues. Well, to make that work, we have to push the different buttons at the right time. And therefore, we need to control, and you must be aware that whatever you do, you need to control your equipment in an integrated way. Because when you want to do something about humidity, you put in more heat, humidity goes down, where the temperature goes up, but then your plants, it costs you a lot of energy. If you want to get rid of humidity, like now in this building, for example, you have to cool it down, and it costs you a lot of energy. But on top of that, if you switch on the light, the plant starts with this photosynthesis that starts absorbing water for irrigation. So you need to switch your irrigation on because the plant starts evaporating. But on top of that, light, photosynthesis needs CO2. So you have to switch on your CO2. So it's not just switch on the light, hope for the best. No, you have to switch on CO2 dosing, control your CO2, control your humidity because the plant starts evaporating. And all in all, it's a whole session of all these different aspects of one single control system, making a climate in a greenhouse and in an indoor farm that makes your plant thrive the way you want as a grower. And like I said, that's not always that the plant can be very easy, the plant can be at ease and it works fine. We have a pear tree in the backyard, and if I want more pears, I have to saw parts off during the winter time. That it's stressed out and thinks, well, I'm going to die, I need offspring, so more pears next day. And then in a greenhouse, compared to an indoor farm, I was thinking about it on the questions I got. If you look into a greenhouse, the weather influences what's going on in your greenhouse big time. So you need to have a weather forecast, for example, and we don't call it weather prediction. That's what you do with a crystal ball. It's a weather forecast. You know how much light, how much humidity will be there, what will be the wind speed, and so on. So you can accommodate for that on beforehand instead of waiting for it to happen. But it can influence relative humidity, your temperature, but also the light levels in the daylight integral for how much light do I need today. It's a dark morning, but I know the sun will start shining the rest of the day. I don't need supplemental light because there will be enough light, even though I don't think so. The weather forecast says it will be the case. We also have a fast reaction of the greenhouse to changing weather conditions. It's just a glass box that sits there outside. So in the winter, we have screens in darker periods. But therefore, we see more and more demand for model-based control, that we know how it's going to behave. But also, we see a trend in the Netherlands to bigger greenhouses. A square meter of air weighs 1.2 kilograms, and that can absorb some heat. So a bigger greenhouse can absorb more heat or release more heat. So you see, and to my amazement, you see 7 meter high gutters in a greenhouse where they grow radishes in the soil. So the plant is about 1 inch, 2 inch, or 5 centimeters above ground, and the greenhouse is 7 meters high. And of course, you don't have so much control for ventilation. You can open the windows, leeward, windward. You can open something in the facade, and then you have to take care of what's going on. And all the models that are floating around in how to do the best ventilation in your greenhouse are struggling with the bigger greenhouses, with all the airflows that go into them. On the other hand, when you look into an indoor farm, and I remember when Leo became professor for indoor growing systems, 15 years ago, I think, and a designated professor, and the discussion at that time was, we just have greenhouses, we switch them on, we do some heating, there were no LEDs, we do some HPS, let's hope for the best. And so much influence from the outside helps the grower or mitigates the problems that the grower induces in his greenhouse system. However, when you go indoors, there's so much more that you can control. You can control the temperature independently. You can control the relative humidity, the light levels, the light colors. You need cooling, limited air speeds, of course. You don't want to rush your air and kill all your plants by having them in heavy wind speeds. And you see a faster reaction on changes because it's a very, very tight, very small section in which you grow usually. So the ventilation control options influence your climate fast. And therefore we see different controls in the greenhouses compared to an indoor farm, for example, with different, tension points for energy management, for boilers, CHP, for which type of equipment am I going to use. And I'm not going to explain this all, but I want to rush you through. If you just think about, I have a greenhouse and I need CO2 and I need some heat. What goes on in the control system to make this work at the lowest energy costs at that moment? Well, that's one back. It's not an easy task to have just CO2 and some heat in a greenhouse. So when you switch to indoor, you can mitigate, you can leave out a lot of these issues. But integrated controls is what I would advocate for big time, and not only because we sell them. And the same goes for water management. If you look into how to treat your plants, irrigation is key as well. When we sit here, we have a nice climate, it's all well air conditioned, but we're all dried out because we didn't have lunch, we didn't have water, we didn't have coffee. The show would be over at the end of the day, I think. And in terms of water management, you need to look into it as a whole system as well, not just irrigation. It's irrigation, it's drain management, so the overwatering of the plants. You give more water to the plants to supply than they need. You give more water than they need to rinse out fertilizer that might precipitate in your growing medium, but also to make sure that every plant in your whole system gets water. So you need drain measurements, you want to think about evaporation, and you want to do some disinfection. When you reuse the water, you don't want the plant that's ill with botrytis or whatever to infect the whole greenhouse within a day or so, and you're bankrupt. And therefore, this is a system, and we can explain it in detail in our booth, but think about water treatment on so many levels. Like you see, we have rainwater, surface water, groundwater, tap water, all with their own peculiarities, so to say, their own challenges. So you might need some pre-treatment to get bicarbonate pH control, and some growers disinfect the incoming water to prevent that the water that came from the neighbor will disinfect their lettuce growing or whatever. Then when you go along the arrow, you see there's a unit for fertilizer injection. Then you go to the plants and you do the measurements, and I'll come to that later on. You do a measurement on how much water is available to the roots and what's the best way to make my plants grow. You do a measurement of the amount of water that's returning, so you have an idea what you're doing in your greenhouse. And on top of that, you disinfect the water that you're recirculating in your greenhouse for what I already said. And according to Dutch law, since 2018, growers are not allowed to flush excess water, so when the sodium level goes up, then your plants will die in the end. And we live close to the sea, just like Panama, so the sodium simply gets in the water one way or another. So when the levels are above a certain level, certain by law given level, growers are allowed to rinse their water to the sewage system. However, when there are pesticides inside, they must break them down. They are not allowed to flush pesticides on the sewage system, so they must break them down. And then we have some add-ons, and more companies do, that break down the pesticides before flushing it to your outside the box that's your greenhouse or your indoor farm operation. We do that with hydrogen peroxide and UV as an add-on. This is what it looks like, so just to show you, these are the schematics, and this is what it looks like when you start building the real deal. Then, looking at the plant, look at what's going on in terms of water. So the plant uses transpiration to cool itself as a pump for fertilizer, for nutrients and so on. It needs some water for the construction of the leaves together with the fertilizer. And, well, what's going on with all the water uptake? So photosynthesis, cell elongation, the cooling, the transportation, like I said. And I think we need to check in or look into detail more also in what's going on in the water. Because we think, and most of the people in the indoor area actually think, you should either do it without any substrate, without rock wool, or have a substrate instead of growing in the soil. But when you do so, you must take care that your plants get the right amount of water at the right time. You want to control the water content in your substrate. So how much water is available to the roots? Do you want them to dry out to induce a different plant build up, a different architecture or something else? So you can stimulate root development if you want to. You can avoid high root pressure, guttation, but also you have to control your HC and your pH in your substrate itself. And by using a substrate, you need to have some more controls than just what you think is right, or just poke your finger in the substrate and think, well, it's going well. Well, that works when you have one plant or 10 or 20, But when you own, like one of our customers, own 97 hectares of tomato plants, you cannot look into one plant. You need so much more advanced technology. And we look into it for when do plants need water? Well, they need it for transpiration, of course, for cooling, transport, like I said. But then there can be a change. So we can give water, we need to give water to the plants when they need the water, instead of that you think, when you think the plants need water. And in order to do so, you must have a sort of model, you must have a clue, what's my plant doing in terms of evaporation. And it can be in an indoor farm, but it can also be in a greenhouse, of course. How do you measure that, and what can you do? Well, there are different devices, and we came up with something. Well, we have a very simple drain sensor, as you can see over there as the gentleman bending over. It's a tipping bucket, it's a pressure loss-free measurement device where we do a measurement of the amount of water that flows into a 2-meter section of a greenhouse or whatever. And you can see we have some scales. And the scales are very precise, that we see every droplet that goes into these specific plants. And by having these scales and having the whole system calibrated for what's dry, what's fully saturated, we can not only see what the plant's doing, but we can measure the moisture level. And we can do it with a sensor, which gives you only an impression of what's going on in this small location, this 10 square centimeter where your sensor sits. Or you can do it much more advanced with what we are in favor of, having these scales and have a large section, so have 2 meters of plants, whatever type of plants, on your system. And like over here, we say, well, we have a type of software we call the moisture balance module, and it's irrigation based on the transpiration of the plant. So it's not based on a timer, it's not based on light levels, so there's more light, so more irrigation. Well, there's more light, but it's a moist day, so why would we give more water? Because the plants cannot evaporate. And over here you can see we sort of mimic what's going on. So you give water to the plant, it starts in the day with dry feet, we all want to go to bed with dry feet, and then it starts growing until we see some drain, we see water coming back, and we keep it at that level until the software decides, based on outdoor temperature, weather forecast, when I stop watering now, I will end at the same level as where I was. And when things change, so when the winds change or the temperature might change, these sessions of water might change as well. And by doing so, you have a correct timing for your first irrigation. You start irrigating when the plants ask for it. You can do it based on what your plants need. And like I said, the correct timing for the last irrigation at the end of the day, so they have dry roots and can take up oxygen at the end of the day and during the night. Well, in order to do so and to go to the next phase, we have, well, just a sort of cartoon made about guided growing. And one of the things I want to discuss, or a peak view for what's cooking in the labs. And I think, well, there's more going on now. The knowledge into the greenhouse industry is deteriorating, so less and less people have a clue how to grow plants, unfortunately. And on the other hand, more and more people go into technology. So how can we make those two worlds meet and we don't starve in between? So if you say, well, let's look at how can we control. So I talked about equipment and everything, and now it's a more philosophical talk, sort of, although I'm not a philosopher. Neither do I have a stone. But we have the plant, then we have a growing system around the plant, and then we have the greenhouse, and we have all the installations that make it work. But the center of our whole operations should stay focused on the plant, and on top of that, on your return on investment, because otherwise it all stops. And then we have the discussion, well, can you grow every plant everywhere? Well, indoor you can, but when you go to greenhouses, we have to check at market logistics. Can I ship out my equipment? Can I ship out my produce? What's the climate? Are there water sources? Are there energy sources that I can tap into? And also, are there financial resources that can help me out? And like you see in the small picture over there, what's driving is the whole system driven by energy? Do I need heating, like in the Netherlands most of the time? Or is water more and more an issue, like in sub-Sahara Africa? So you can see a sort of mimic for around the equator, it's water, or is it something else? And depending on what type of system do you want, what type of greenhouse do you need, and that's, well, like a real estate, location, location, location. Well, that's the same applies for a greenhouse. This is a greenhouse in Costa Rica, and building a greenhouse like this in the Netherlands wouldn't work. Building a Dutch-style greenhouse in Costa Rica would work, but you would never have a return on investment at all. With the moist climate, the high temperatures, the heavier rainfalls that were going around when I took this picture. So you have to check out what's going on and even think, do I need a greenhouse? Where are my resources? Can the government help me out? So starting and is where do I go? What do I do? And then the installations, well, check out what you need. Look into the GPS coordinates, type of greenhouse, and so on. Water, climate control. And look into operation. We have a saying in the Netherlands, not every road leads to Rome, which is not so very logical when you're in Panama, but in Europe it made sense 2,000 years ago. So you have to check how do I tune my operation one way or another. So like I said, have your homework done and look at your climate, the local climate, the climate you want to achieve, but also what's feasible. I had some discussions 3 weeks ago with people who said, well, I want a research greenhouse and I want 5 centigrade in my greenhouse when I want to do research. But I said, well, how much sense does it make when it's outdoors 30, 35 and you want to build a cooling system that goes all the way down to 5. So adapt your technology, adapt your tests and the research you do to the outdoor climate as well. In winter you do low temperature sessions, in summer you do high temperature sessions. And what's the pricing of your resources? And we think we need artificial intelligence in horticulture, so Ag 4.0. But the domain is somewhat difficult from other types of technology. They're costly resource-driven systems, the whole infrastructure, the greenhouses, everything that goes around it, and usually they're family-owned. Like I already said, they're very susceptible to climate changes in the weather. It goes very fast. There's a variety in systems, installations, and greenhouses. Every grower wants the greenhouse that he thinks is best, and it's highly integrated. So we have to check, and I'm not going into detail for this, but for having this type of artificial intelligence, self-learning system based on big data, you must have environmental awareness. So where are you, which crop? What are the interactions, like I already pointed out? How do you want to do your control? Do you want to have it a section that's learning just by doing so, or messing around, making mistakes? And what type of autonomy do you want in your control? And it must run 24/7. It's not like a factory, like a welding robot that you switch on and it's 5 o'clock, you switch this factory off, you go home. But the plants keep on growing or they keep on dying when you don't pay attention to it. So there's so much coming into a company like us for thinking about how do we adapt to this whole torrent of data and all the ideas that go around. So what type of knowledge do we need? Model-based architecture, intelligent engineering tools, and then on top of that there's so many platforms in terms of technology. Some are outdated. Microsoft changes its policy time and again, and when you're dependent on that, you're in trouble sometimes. And last but not least, internet security. When somebody hacks your greenhouse, what's going on? Is that what you want, that somebody else takes care of your tomato crop? Or have ransomware or whatever. And then we have a sort of in-between. So on the one hand, we have the plants, And on the other hand, we have the control systems. And the plants are individuals, every plant. They're complex, they're dynamic, and they are also time dependent. So when something goes wrong today, you cannot find out, but you find out a week later that something went wrong a week ago, for example. So these time dependency in your crop, in your whole development, is part where you have to think of. But then the controls, we must have very precise models to deal with all these differences and everything. But they also must be compact, because if you have a large system and it takes a day to generate the data for how to control for the next 5 minutes, then you're in trouble. So it must be a compact system that keeps on running. It must be dynamic, because everything changes. And it must take care of the different systems, the different varieties in how things react. A plant reacts slow, your water system reacts within 1 to 2 hours, but your climate can change within 5 minutes, for example. So we have to deal with problems that are not simply put into differential equations. And we have these sections. So we have to learn and adapt. We must make complex decisions. It must contain expert knowledge, and that makes things much easier. And you want to handle uncertainty in one way or another. And then we have some issues on top of that. Vague goals, differences, and nonlinear process behavior. You never know what will be the next problem that you'll have to. So machine learning, it seems to be the next big thing. It seems to be an easy step. Less engineering, better controls. But there are some things to think about. Are machine learning control systems allowed to make errors? When you look into a robot, I know in Delft University of Technology, they were defining and building a robot that could walk on its own. So you put a robot on the floor and you said, well, just start walking. And then there are learning and there are all types of regulations in the software that make the robot work at the end of the day. But it can take a day or 2 days or 3 days, and in the wrong situation, the robot or the software comes up with a solution that you never thought of, that the software decides, if I stay put, I won't fall, I won't have any issues, so why bother starting walking, for example. So how much room is there to make errors? And you don't want a lot of errors when you're growing lettuce, and you just had, like plenty, have your $100 million check cashed. And you think, well, let's start in machine learning and see how it goes. And when 10 mils are down the drain, you think, well, maybe you should change something. So how much room is there to make an error? How good is it to maintain and to keep it stable over the time? Because your next phase in growing, you clean out your greenhouse, you clean out your indoor farm, and you start all over again. And indoor is much more defined than a greenhouse, but nevertheless, how much errors can you take? And also, are the sessions that you run in how to find a solution, is it really the best solution, or is it just something that the mathematics give you an idea that it's best solution, but like we said over here, it's more tech speak than growing speak. Is the area convex enough? Are we somewhere up the hill on a plateau where we think it's good, or are we really at the optimal level where we think we should be? And on top of that, as a reminder, 2 years ago we had Dr. Greenhouse on stage over here, Nadia Sabah, and we as a company as well, don't forget the psychromatic chart, the basis of all HVAC. And on the left is the European version, and on the right-hand side, you see the US version. I never get it why it should be this way. It makes things so much more complicated, apart from the empirical units and all the issues that come with that. So, a lot to digest, and maybe too much, but, well, better safe than sorry. Thank you.
Dankjewel. Thank you. So questions again, and some of the students are here if you guys would like to ask. There we go, there's one. Jan, I have a very, very quick question while these guys get it. When we talk about airflow, we talk about moving a plant, We talk about strengthening the cellular walls of the plant through airflow. Is there an optimum airflow speed depending on the plant?
Well, that's one of I think that's a PhD problem, sort of, because there are different sections. It's not to answer your question, but if you look into a leaf, there's a small boundary layer that keeps the plant in where it is. So when you have a high airflow, we saw it in the closed greenhouse in the Netherlands first time. When there's a high airflow, all the leaves dry out and they simply get brown and they die. Where the plants keep moving too much, there's too much stress and sometimes it doesn't work. We saw that we had some growers who said, well, why don't we build like dwarf weeds? Why don't we build dwarf tomato plants and keep them moving all the way through the greenhouse and bring them to the barn, and then we pick all the tomatoes and we start all over again. And that didn't work because of all the airflow, all the stress, the extra stress.
So there's such a thing as too much airflow.
Definitely, yeah.
Okay. Thank you. A couple questions here. First one is, how can we check or control the irrigation in an aeroponic system? Aeroponics, for those that you don't know, is a misting system, not deep water or...
Yeah, that's a trick question. I will ask the guys from Aero Farms tomorrow. I have a conference call with them.
That's right. If you have somebody from Aero Farms here, raise your hand. There they are. Okay, you can help us maybe.
No, but for now, well, the only thing that you could think, like Leo was talking about, you have the root-shoot development, so how much water goes into the root, how much goes into the shoot, so shoot root, that's how I should point out. And by doing so, you can have a measurement of the amount of growth of the plant, but like we do with these scales, it's not possible, so you need something else to attach to the plant. And I've seen, long time ago, some small devices you can clip onto a leaf and see it's the turgor layer, the turgor, so what's the cell tension. And when you see that going down, you know you have to react. But that's a 1-point measurement instead of doing 10 plants or so. So that might be one of the minor solutions to do so.
Okay. The next question is, how do you manage CO2 levels when you go from light to dark period and the plants release CO2 instead of absorbing CO2? Want me to repeat that?
Yeah, no, I got it.
You got it?
I got it, but maybe...
Yeah, how's our translator doing on that one? How do you manage CO2 levels when you go from light to dark period and the plants release CO2 instead of absorbing CO2?
Well, I'm just a humble mechanical engineer, but looking at the balances, I would say that a plant that absorbs CO2, it makes sugars out of it, it makes itself out of the CO2, so it's part of the construction. So the CO2 that's released in nighttime is much less than the CO2 that's absorbed during daytime. Apart from that, so it's so much less that can help. And there's just some minor ventilation. And usually, especially in an indoor farm, a greenhouse always leaks to a certain extent. In an indoor farm, you want to have these dark periods as short as possible. So you're aiming at 8 hours, 4 hours, so then the CO2 build up, if it's available, won't be an issue at all, I think.
Okay. And one other question here. See if I could read this.
Just, what do you call it? I'm in between two academic powerhouses, so whatever I say can be changed in the next talk. So
we understand. The question is, the change of water, is the change of water temperature, or does the change of water temperature affect nutrient absolving or assimilation, if I'm reading that correctly?
Yeah, it does. And well, I have some talks. We have a plant scientist in our company, and we talk plants, and I don't know so much about plants. I said, well, I have a hunch of thermodynamics. And on that approach, when your feet are warm, it gives you a hard time to get everything up. So warmer roots, and it's the same, warm water cannot contain so much oxygen and so ever. So the whole chemical stability can change when you heat up or cool down your water. And on top of that, we have some indoor farms ourselves where we run tests, and where you have a system where you keep on putting pump energy into the water by pumping the water around, running it through drippers, all the energy, most of it that goes into your pump, goes into the water, heating up the water. So what we do in our indoor farms, we add cooling systems for the irrigation water actually, because warm roots don't work well for the plants. And the oxygen, well, we have hydronics in the Netherlands, so central heating, and it goes to 90 C, and there's no oxygen in the water at all. And therefore you can use just simple piping, because it won't corrode on the inside, because there's no oxygen, because the temperature is so high.
Last question happens to be from me. So if you all don't know about the Priva Ocado 80 Acres Farm collaboration, I would like you to just say a word or two about that. For those of you that are aware of 80 Acres Farm, it's a farm in the United States that has actually about 5 or 6 farms. And like many outdoor farms, they've been moving to indoor growing for germination and propagation. The Ocado piece of this is fascinating to me. For those of you that don't know, Ocado creates bots and machines to move product, and it's fascinating. Can you say a few words about that, Jan?
Yeah, just a few words, yeah. Well, to be fair and square, I'd never heard of Ocado as well until we visited them. And it's by far the largest retailer through internet, I think. They have a section for frozen foods, for commodities, and for fresh foods. And Ocado is looking into, and actually, well, rewind, and every new section they build in terms of warehousing and packaging and shipping, they want to go to the next level. So they thought, well, we must look into how can we operate, get better fresh foods close to our big operations instead of trucking it in. On top of that, we have a collaboration. Well, Mike Zelkind was quoted already, but 80 Acres Farms is an endeavor, a company in Cincinnati, Ohio. They have a small farm there, and they are in the phase, as we speak, of constructing big farms. They also go to different states. And they come from a different angle. So they're not plant scientists, although they hired them, but the entrepreneurs are people who are very well founded in logistics, in food logistics, and how do we sell all the foods, and how do we truck it out, and so on. So they looked into what's the difference between a crop of lettuce or a piece of lettuce, a head of lettuce that comes all the way from Salinas, 6,000 miles, grown and breeded for transport, compared to a head of lettuce that you grow 50 miles away. So can you charge more? Is it fresh? And so on. And they found in that whole area, although it's part of the Rust Belt, they found a large community or people who are willing to buy that. So 80 Acres Farms will be the operator. Ocado will be part in several sections of the world, sort of the company that buys it from the operator, and we are the tech supplier. So we can do the controls, and we do turnkey growing systems with infinite acres.
Can we get one more round of applause for Dr. Vestra? Thank you.
Okay.
Okay. Everybody feeling okay? Everybody feeling all right? Good. You're paying great attention. Thank you very much. Gracias mil. All right, so from the Netherlands, we are now going to upstate New York. Anybody been to upstate New York? It's cold there. It's very cold there. We have a friend here, Dr. Neil Matson. Dr. Matson joined Cornell University in 2007, having previously earned a PhD from the University of California, Davis, and a Master's of Science at the University of Minnesota, another very cold place. He is currently an associate professor and director of Cornell's Controlled Environment Agriculture Group. His research focuses on physiology of plants in controlled environments, especially strategies to reduce energy use, LED lighting, nutrient management, and abiotic stress physiology. He has authored 46 peer-reviewed journal articles and given more than 250 outreach presentations to 10,000 agriculture industry members. Please welcome Dr. Neil Matson from Cornell University.
Thank you, Jen.
Neil, all the best. There's your clicker right there.
Thank you. Good afternoon, everyone. Buenos tardes. So for my presentation for today, it's going to be fairly practical compared to some of the talks. We're going to talk about the basics of mineral nutrition and fertilization, some good strategies for diagnosing nutrient disorders, talking about then specifically for leafy greens and herbs, what are some of the more common disorders, and then the causes and how to correct those problems. And then we'll finish with talking about some of the more common disorders of vine crops, such as tomatoes and cucumbers. And I don't expect you to memorize this whole list, but anytime I give a talk on nutrition, I'd like to remind us that there are 14 different mineral elements that we have to be sure the plant is supplied, right? So nitrogen is needed by the greatest quantity by the plant, and some of these things like molybdenum, we need 1 million times less. But they're still very important for the plant. So even these micronutrients, the plant cannot complete its life cycle and have proper yield without having the sufficient quantity of those micronutrients supplied to the plant. So a little bit about the basics of nutrition. When we look at these different nutrients, some of them, such as nitrogen, phosphorus, potassium, and magnesium, we refer to these as mobile nutrients. These are nutrients that can move around within the plant through the phloem. So even after they've been set down into the leaf, the plant can scavenge them from old tissue and send them up to new tissue. So this is very important when we're diagnosing nutrient disorders, because if a plant becomes deficient for one of these phloem mobile nutrients, the deficiency symptoms are going to occur first on the older leaves. So that is the plant is going to scavenge or draw on the nutrients from the older leaves and then ship them in the phloem to get to the top of the plant, to where the stem is actively making new cells. For immobile nutrients, these would be the opposite. So some examples of these are boron, calcium, copper, iron, and manganese. And for these nutrients, they are not really phloem mobile, or not very phloem mobile, so the plant can't take them from old tissue and give them to new tissue. So for this example that I have here in a photo for iron, if iron becomes unavailable, such as from high pH in the root zone, the part of the plant that's still growing, the shoot tip, is still going to need iron, but it can't get it from old tissue. It can't scavenge iron from the old leaves and send it to the new tissue. And so what happens is that the deficiency symptoms are going to show up first on these young upper leaves. To summarize, if we know whether a nutrient is mobile or immobile, that can help us to diagnose where we first see the symptoms of the disorder. So for the bottom of the plant, we will see deficiencies of mobile nutrients, nitrogen, phosphorus, and so on. In the top of the plant, we see these deficiencies with calcium, boron, iron. And then in the middle of the plant, we have a couple nutrients which are partially mobile. So they can be somewhat scavenged from the tissue and sent to other parts of the plant. So for sulfur and molybdenum, we see deficiency symptoms that show up in the middle of the plant, often like those most recently expanded leaves. And then in the case of sulfur, we also see often that we see a yellowing of the plant as a whole, not just the bottom or the top of the plant. Nutrient solubility, or the ability of a fertilizer salt to dissolve in water, is also a really important property. So when we're mixing up fertilizers, especially when we mix them in concentrated stock solutions, it's very important to make sure that we're not past the limits of solubility. And like we have in this chart here, we have several different fertilizer salts that are listed, and then we have their solubility at different temperatures. And so the solubility will go up as temperature increases, which is great for mixing up the fertilizer, but then you can't count on, once that water would cool down to room temperature, that's the solubility that we really have to look at to make sure that the fertilizer salts that we mix together are going to stay soluble. And nutrient solubility in our fertilizer solution is also a function of pH. And so this graph shows pH as we go from a pH of 4 on the left to a pH of 8 on the right, and then how soluble is that nutrient. So for like nitrogen and potassium, we're very lucky in that nutrient solubility is broad, is good across the pH range from 4 to 8. For elements like calcium and magnesium, we lose solubility as pH drops down below about 5. And then there's this large number of micronutrients like iron, manganese, and boron, where solubility really goes down dramatically after a pH of about 6. So because pH affects nutrient solubility, we need to adjust our nutrient solutions. Typically for lettuce and herbs, we're looking at a pH of about 5.5, and for tomatoes, a pH of about 5.5 to 6. If you're growing in a hydroponic type situation, or a situation where you have an inert substrate, such as rock wool. With iron, there is different types of iron that can be used, and typically we're using different types of chelated iron. And what chelated means, chelation is a large molecule that wraps around the iron, and it keeps it soluble across a wider pH range. So on the top of this graph is one of these chelating agents, EDDHA. It's actually soluble across a very broad pH range. We have soluble nutrients. Some of these other chelating agents like EDTA, the solubility is pretty good till about a pH of 6.5, but after that the solubility rapidly declines. So that is, you might think you're adding iron to the nutrient solution, but if the pH is not appropriate, the iron's actually not soluble in nutrients and then available for a plant to take up. When we mix different fertilizer elements together, we also have problems with incompatibility. So some of the fertilizer salts that we mix together are not compatible in a concentrated stock solution. In this case, they will precipitate out. And this is an example where we mixed 2 different fertilizers that were not compatible. On the right side is where they're mixed at a 200 times concentration, like they would be in a stock solution. And so this sludge or this precipitate forms, and that can clog up our injector line and make these not soluble and not able to be taken up by the plant. There's quite a few different incompatibilities, but the most common one that we have to worry about is that calcium is not compatible with phosphates or sulfates. So we have to make sure that we don't combine calcium nitrate with phosphates and sulfates. You can find these different charts online with fertilizer compatibility. So this one would show us, for example, if we look at the row for calcium nitrate, it's not compatible with potassium sulfate, ammonium phosphate, our micronutrient sulfates, etc. And because of the issues with incompatibility in our stock tanks, then we need to use multiple stock tanks so that we can then use injectors to dose out these nutrients and blend them together at the dilute form that the plant is able to get. Typically in these, we have the first tank, like tank A is calcium nitrate. Tank B would be the things that are not compatible with calcium nitrate, such as phosphates, sulfates, and micronutrients. And then often we add a third stock tank to control for the pH. So most commonly, if we're using a nitrate-based fertilizer and our water source has, say, some carbonates or bicarbonates, some alkalinity in the water, the pH of the root zone is going up over time, and so we need to add acids, such as sulfuric acid, to control the pH. And so this is just an example that will go in the different stock tanks. So tank A for calcium nitrate and compatible salts, tank B for sulfates and phosphates, and then tank C for adjusting the pH. So I want to move next to talk about different tools for diagnosing nutrient disorders. So some of the simplest tools that we have available to us are handheld meters like pH and electrical conductivity meters. Then we can progress. We'll talk a little bit about laboratory analysis, and then some of the visual symptoms of nutrient deficiencies. So as we discussed the issues with pH and solubility, we want to, of course, test our pH every day in a hydroponic production environment, if not testing it continuously with a more automated system. So a high pH is going to limit the solubility of iron, manganese, boron, zinc, and copper, and that can be one of our large indicators that we can expect this micronutrient deficiency. So that can help with the diagnosis. A low pH, such as less than 5, may cause a deficiency of calcium or magnesium, or occasionally the plant could actually take up too much of these micronutrients like iron and manganese when we have a very low pH. So sometimes we can see a toxicity under very low pH conditions. The electrical conductivity is a measure of all of the salts that are dissolved in water, which are the fertilizer salts as well as the non-fertilizer salts. If we have a relatively pure water source, then the electrical conductivity correlates very closely to the overall fertility that we're providing the plant. It still doesn't tell us what the actual composition of the different elements are in the fertilizer, which is why a laboratory analysis is important. So a low EC, so below crop-specific thresholds, means that we do not have enough fertilizer getting to the root zone of the plant. So we're giving the plant not enough fertilizer. If we have a high electrical conductivity, it would mean that we're adding too much fertilizer. So it could be that we're over-fertilizing our plant. We're giving the plant more fertilizer than it can use according to its crop demands. It could also be that we have insufficient leaching. So it could mean that we have not giving enough water to leach out excess soluble salts in the root zone. And so then we have salt accumulation in the root zone. The units that we use for electrical conductivity, they can be confusing. As scientists, we use the unit decisiemens per meter. This is the same as another of the common units that are commonly reported, which is millisiemens per centimeter. And this is 1,000 times more than microsiemens per centimeter. So for lettuce in a hydroponic nutrient solution, our EC targets are typically 1.4 to 2.2. Depending on the fertilizer recipe. And then this would be also added to the EC of the water source. For tomatoes, our EC target in the nutrient solution is often about 2.6. You can actually do some adjusting based on the crop stage, and I'll give some examples of adjusting the fertilizer solution for tomatoes later. And then, so that's of the nutrient solution that you're delivering to the plant. What's actually building up in the root zone, according to the pattern of supplying irrigation water and leaching, is that the root zone EC might be about 4.0. For cucumbers and peppers, the actual fertilizer will be somewhat similar to tomatoes, so an EC of 2.2 in the nutrient solution, but we won't let the root zone EC build up as high as tomatoes. So our typical EC in the root zone will be 3. So pH and EC are relatively simple and affordable measurements that you can take in-house at your own operation. However, they don't really tell us about the individual nutrients that are in the solution. And so in that case, we need to use a laboratory analysis. It is important still when you start using a new water source, to analyze the water source so you can determine what nutrients are in the water already, what are the possible problems with salts that can develop. And then even after you've mixed up the nutrient solution, maybe you think that you have mixed it correctly, but maybe there's problems with the equipment or there were problems with precipitation. So it's still important to actually periodically measure the fertilizer solution and make sure that what the plant is getting and what the plant will continue to receive in the future is what you want it to be. So when we measure the laboratory analysis for water and fertilizer, in a sense it gives us a window into the future. This is what we're going to be delivering to the plant, and that can help us to make changes before we even start growing the plant. You can also test the substrate, which is a nice reflection of what the plant is currently getting in the present, and it can tell us how the fertilizer we're using, how closely that actually matches to what the crop demands are. And then the tissue tells us what is actually in the leaf of the plant, right? The great thing is that tells us kind of the integration of the nutrients that we supplied, the root zone conditions, and what the plant actually took up based on the environmental conditions. However, that's a reflection on past practices. So if we want to be proactive, we're trying to solve nutrient disorders before they show up in the tissue of the plant, in which case the yield or the quality of the product may already be affected. Tissue testing is important because many of these nutrient disorders can look the same. And so if we are noticing a problem in the plant, a visual problem in the plant, the idea is that we'll take several leaves that express those same symptoms and pool them together into one sample that we send to a lab for analysis. Especially when it's a problem that the lab has not seen before or that's new to you. If you can also send some leaves to the lab that are from control plants, meaning they're not affected by the nutrient disorder, even though they're from the same age leaves, that can sometimes help in detecting what is the real problem with the plant. In terms of tissue testing on a regular basis, or proactively tissue testing even before visual symptoms have occurred in the plant, the idea is to take several of the most recently expanded leaves, and these would be from several different plants that are representative plants created across the entire greenhouse crop. You would do this every couple of weeks. And for some of like the vine crops, for example, you can look at key developmental stages, and laboratories will have recommendations on these developmental stages in which to send tissue samples to the lab. So in this scheme, for example, this is an example from a tissue testing lab in the US. You're sending some samples to the leaves when it's at the young transplant stage, when it has 4 to 5 true leaves, when it's first getting established, when you have the first flowers at anthesis or shedding pollen, and then further as the crop continues to develop and enter into the fruiting stage. For these common crops that we grow in the greenhouse, the commercial testing labs are going to have sufficiency ranges. So these are suggested values that the nutrients need to be so that we don't see disorders on the plant. So here's an example for tomatoes, for nitrogen. In the early fruit set stage, nitrogen should be sufficient if we have 4.5 to 6% nitrogen. At the mid-harvest stage, the plant's drying up, somewhat more nitrogen, and so we're trying to maintain nitrogen to be between 4.5 to 5.5%. So here's examples for tomatoes for macronutrients. For the micronutrients, we also have these suggested sufficiency ranges. And then this would be a lot of numbers, but for some of the common leafy greens like lettuce, as well as for herbs like basil, these commercial labs will have suggested sufficiency ranges for the macronutrients and micronutrients. So when you get the report back from the lab, they can tell you, were you on track? You can try to look for patterns. So if several of the macronutrients are low, for example, that would suggest we're just not supplying enough fertilizer to the plant. If just one specific nutrient is low, it could mean that we're just supplying our nutrients out of balance to the plant. So maybe the plant is using something like potassium in greater quantities than we're actually supplying to the plant. So then this can help us to adjust our nutrient solution and to take corrective actions. So next I want to move into talking about visual diagnosis of nutrient disorders, and then we'll talk about some of the more common issues in both leafy greens as well as vine crops. So when you notice that your crop has a problem, we want to visually inspect it, and you can learn a lot about what is happening based on the patterns that they show up on the plant. One of the first things that we have to do is decide, is the problem happening due to pest and disease, or is the problem happening due to nutrient deficiencies or other abiotic disorders? So when the problems are due to pest and disease, some of the things to watch out for are the symptoms are spotty, meaning some plants are affected and other plants are not affected. So maybe if there's a particular pest issue, one plant is kind of in this hot spot, it's the most affected plant, and then some of the neighboring plants around it are starting to get affected by that pest. If you look at the leaves themselves, the spots on the leaf of the disorder are typically not symmetrical, so they're not consistent throughout the leaf. What's happening on one side of the leaf may not look like what's happening on the other side of the leaf. So that's our indicator that something related to biology is the problem, so like pests and disease issues. If the problems are related to abiotic disorders, so things like nutrients or the environment, the symptoms will be symmetrical on a leaf. So what's happening, what the symptoms look like on the left side of the leaf should look closely to how the symptoms look on the right side of the leaf. The patterns are also going to be consistent throughout the crop. So for example, if we're just not supplying enough nitrogen to the crop, we're going to see that fairly consistently on all of the plants of the crop, and kind of the same age leaves are going to be affected. I have some different resources that I developed for lettuce and basil for visual diagnosis of nutrient disorders, and I'll show some of those pictures when we talk about examples. The main website to go to is called egrow.org, which is e-grow.org. For tomatoes, I don't have my own photos, so Haifa, which is a common fertilizer supply company, they have a very nice online guide to some of these nutrient deficiencies in tomatoes. And a little bit about the vocabulary, at least English vocabulary. When we talk about chlorosis of leaves, this is leaf yellowing. Necrosis is tan or brown leaves. So this is when we actually see like tissue death on the plant. So those parts of the leaf have turned brown. We'll call that necrosis. And then in terms of the location on the leaf, some of these deficiencies show up on the edges of a leaf, which we call marginal. So we might talk about marginal chlorosis, meaning yellowing at the edges of the leaf. And then interveinal means the region that's between the veins. So some of these deficiencies show up between the veins of the leaf. So we might call that like interveinal chlorosis. And then when we think of like calcium or boron, the symptoms that we see might be more like leaf distortion, which are incomplete leaf expansion. And so we have leaves that are distorted or disfigured in their appearance. And they might be strap-like, so they might be like long, thin leaves instead of a full leaf. When we're thinking about whether the cause of a nutrient disorder is actually coming from the fertilizer solution or from the growing environment, we do need to think about other causes of these nutritional disorders. So sometimes they can just be caused by poor weather. For example, under if we are adding some ammonium to the hydroponic nutrient solution, we rely on having a relatively warm root zone to promote the development of mineralizing bacteria that will convert ammonium, which can be harmful to a plant in high concentrations, into nitrate. That we can also see problems due to poor drainage of a container. So if there's just not enough oxygen in the root zone for good root growth and respiration, that might also show up on the plant symptoms as like a nutrient deficiency. So over and under watering, so we'll talk about calcium disorders and blossom end rot. Under conditions of low light, the plant also might not have enough photosynthase to promote good nutrient uptake. Nutrients can be tied up by the growing media, and then sometimes having too much of one nutrient can tie up the uptake by other nutrients. So a nice example of that, if we have too high of like chloride, for example, nitrate uptake can be reduced, or if we have too much sodium, calcium and magnesium uptake could be reduced. And so poor water quality, such as high sodium and chloride in our water, could be one of those causes of nutrient disorders. Just as an example, these are photos of basil, so a common herb that suffers from iron deficiency. And if you just look at the leaves show us yellowing between the veins on the upper leaves, which is symptomatic of iron deficiency. But the actual cause is from this root disease. So the roots in this case were infected. There was insufficient rooting and then insufficient uptake of iron, which was showing up on the leaves of the plant. So then let's talk about some of these common disorders, first for leafy greens and herbs, and then we'll be talking about vine crops. So one of the common nutrient deficiencies that I observe, especially in basil, is magnesium deficiency. And so magnesium deficiency shows up as yellowing between the veins of old leaves. So if we look at this, this basil plant, for example, on the left, it's really that old leaf that's affected. And the young growth is showing no problems at this point. We have a head of lettuce on the right side, and it's also showing us the interveinal chlorosis on those old leaves. So why do we see this problem with magnesium deficiency? Occasionally it's due to low pH. Like I was talking about earlier, if pH is less than 5, we can sometimes see a magnesium deficiency show up. More often it's due to just the lack of magnesium in the nutrient solution. And what we find is many growers are growing both lettuce and basil in the same hydroponic nutrient solution. However, basil seems to have this higher need for magnesium. So while 30 to 40 parts per million magnesium may be sufficient for lettuce and leafy greens, basil we need to have more like 60 parts per million magnesium. Iron deficiency. So iron deficiency also looks like yellowing between the veins. However, it's the young leaves that are affected. And remember, this is because iron is one of those immobile nutrients, so it can't be scavenged by the old tissue. So when it shows up first on the younger leaves of the plant. In the case of iron deficiency, usually the problem is not that we don't have iron in the nutrient solution, but that we have a high pH, which limits the solubility of iron. So first is one should check and correct the pH and make sure that the pH is suitable for the crop target. So for leafy greens and herbs, often a pH of 5.5 to 6. And then if pH is appropriate, but we still saw these problems with iron deficiency, then for sure check the actual iron concentration in the nutrient solution. This should be 1 to 2 parts per million for leafy greens and herbs, and 2 to 3 parts per million for tomatoes and other vine crops. And using a chelated iron form will make iron soluble across a higher pH range. Not very commonly do we see nitrogen deficiency in lettuce. However, I see this sometimes in like an NFT system. So maybe in your NFT lettuce system, you have a fairly small volume of water compared to the number of plants that you have. Maybe you're adjusting fertilizer according to EC. And if the plant is using up more nitrogen than what you're supplying in the nutrient solution, the EC may be fine because other salts have built up, but nitrogen might be low. So in the case of nitrogen deficiency, the symptoms are yellowing of the lower leaves. We'll also see that the plant size can be much reduced. This is typically a problem from not enough nitrogen in the fertilizer. Then I want to talk about leaf tip burn. So for head lettuce, this is a very common disorder. And the symptoms are we have necrotic regions or brown leaf edges on the tips and edges of young leaves. It's usually it is the center of the head that is most affected. And the crops that are affected are head lettuce. The causes of leaf tip burn, it comes from calcium deficiency, but usually there's plenty of calcium supplied in the nutrient solution, and the problem is more due to physiological disorders. So with calcium, it's one of the nutrients that we actually need active transpiration by the plant to promote uptake. And if the plant is growing too fast as the head reaches maturity, the roots might not be able to take up enough calcium. It can happen when we also have conditions that give us poor transpiration. So if we have very high humidity and poor airflow, that can also drive this leaf tip burn. So the solutions are to decrease relative humidity or increase vapor pressure deficit, install greater airflow. And so for head lettuce, sometimes what are used are vertical airflow fans, which are actually directing air down vertically onto the tips of the lettuce heads. Also, the problem could be that we're growing the plant too fast, so we need to decrease light levels. Sometimes we see this problem occur under summertime conditions of high light if we don't have enough shading for the greenhouse situation. One more physiological disorder that we'll see for lettuce is outer leaf edge necrosis. So this occurs on the outer leaves or the old leaves, not on the inner leaves. And in this case, we see these brown spots that happen on the leaf edges, and it happens on the hydathodes, which are the part of the leaf where the veins end. Head lettuce would be affected in this case. The causes of this are guttation, which are leakage of water out of the veins, where the veins terminate in the leaf at the hydathodes. And the causes of this can be high relative humidity at nighttime, or maybe those fluctuating conditions. So if we had high relative humidity and poor airflow at nighttime, and then all of a sudden the daytime comes and we have low relative humidity. So we want to avoid conditions of high relative humidity at night. Also high EC of the nutrient solution can also drive this. So last, I want to look at some of the common disorders of vine crops. So potassium deficiency is one of the more common deficiencies that shows up in tomatoes. And the symptoms are affected on the older parts of the leaf. And we have this leaf edge chlorosis or yellowing, which can proceed into necrosis. And then as the potassium deficiency further advances, you can actually get necrotic spots between the veins of the leaf. This shows up on the fruit as this disorder that we call either yellow shoulder or green shoulder. So this is the upper part of the fruit near the stem is affected. It's yellow, so instead of the fruit uniformly ripening to be red, we have this yellow or green shoulder, we call it. And if you cut open the fruit, you can also see that inside of the fruit we don't have good uniform red coloration. So this is usually due to lack of potassium in the nutrient solution. And when these vine crops are in their fruiting stage, they have higher potassium needs. The potassium in the tissue should be at least 3% at fruiting, so it's important to do these laboratory tests of the leaf tissue. And also, sometimes if we have too much magnesium, that can antagonize potassium uptake. So we also want to make sure that there's not too much magnesium. Typically, once we're in the fruiting stage for these vine crops, we make sure that there's 350 parts per million of potassium in the nutrient solution. And just a little bit about fertilizer recipes for tomatoes. So we typically divide fertilization into at least 3 crop stages. Sometimes you can see recipes where they divide it into 5 different crop stages. And this recipe comes from the University of Arizona and their CEA group. So they have tomatoes at stage 1, which are at the young plant stage, so the seedling stage, until the plant has the first or the second flower at anthesis. Then the second stage is this intermediate stage, where the plant is in this transition from vegetative growth into fruiting. And then the third stage is when the 5th truss or the 5th flower cluster is at anthesis, and then beyond while it continues to fruit. So the things that we adjust in the nutrient solution are that nitrogen, we initially have that low because we want to encourage generative growth to the plant. So we're steering the plant to go from the vegetative stage to the reproductive stage and to make flowers and fruit. Then once the plant is in that reproductive stage, we want to increase the nitrogen concentration because the plant is going to have higher nitrogen demands at that fruiting stage. As well, when that crop is at the fruiting stage, we need more potassium and we need more calcium. So if we look at this fertilizer solution, you can see that nitrate on the top, when the plant is at the stage 1, we're only adding 90 parts per million nitrate. By the time we're at the final stage, we've increased the nitrate to be 190 parts per million. Potassium increased from 144 to 350, and then calcium also increased somewhat from 144 to 200 parts per million of calcium. And in these recipes, the other nutrients stay the same. One of the common vine crop disorders is blossom end rot. So this is the terminal end of the fruit, shows this necrotic regions or cell death. This is also a calcium deficiency. This one is usually due to poor transpiration, which may be due to water management. So often we see this if the root zone has been allowed to dry out too much. The roots lose contact with the soil solution, and they're not able to draw up the calcium that they need through transpiration. So that might result then 3 or 4 weeks later as blossom end rot that will show up in the fruit that had been just at the very beginning stages of development when the drying out occurred. Transpiration is important to drive calcium uptake. So if we don't have good airflow, or if we have too high of relative humidity or too low of vapor pressure deficit, that can also be related to blossom end rot. So more examples of blossom end rot. On the leaves, the symptoms show up on the young leaves, and you see necrotic edges of the leaf, and sometimes we see these leaf distortions. Because calcium's an immobile nutrient, it can't be scavenged by the older tissue. Calcium's needed as a component in new cell walls. So if we look at the growing point of the plant, the apical meristem, calcium's needed as a cement to glue the cell walls together. So then, as I mentioned, we need active transpiration to drive calcium uptake. We do want to ensure there's adequate calcium in the fertilizer. This should say 200 parts per million calcium at the fruiting stage. Careful irrigation management, make sure the substrate is not drying out, and then promoting good transpiration by the plant. Then magnesium deficiency, we also sometimes see when the plant is older and in the fruiting stage. Magnesium deficiency for tomatoes also looks like yellowing between the veins of the old leaves. Cucumbers are very sensitive to magnesium deficiency, and you can see it's the lower leaves on this plant, the older leaves, that are showing the yellowing between the veins. So correcting magnesium deficiency for these vine crops, usually it's not due to low pH, but you should check the pH and make sure that it's not too low, such as below 5. Usually this would be from a lack of magnesium in the nutrient solution, or maybe there's too high of calcium or potassium. So we want the calcium and magnesium ratio to be about 3 parts calcium to 1 part magnesium, up to about 4 parts calcium to 1 part magnesium. And the solution is to add additional magnesium, often through magnesium sulfate, to a target of about 60 parts per million for vine crops. Okay, so that was a whirlwind tour of different nutrient disorders in vine crops. And with that, I want to thank you and welcome any questions.
Thanks very much, Neil. Ron, check, 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 check. Check, check, check. Check, check, check. Check, check, check. ¿Me oyes? Por favor, ¿me oyes? Ya, ya. Hello?
Do you want to use my wireless mic? Yeah.
Okay, thanks so much, Neil. Appreciate it. Yeah, we got the sound going.
We got it.
Yes, sir. Let me just pull this off my face. Neil, thank you. Again, questions, guys, but let me share a quick thing that I want to do today in an effort to speed up time and also to kind of help you guys a little bit with some more networking this afternoon. So what we're going to do is we're going to go right to Dr. Ricardo Hernandez after any questions for Dr. Mattson, and then from there we'll have a coffee break and networking, and you'll have as much time as you need. So we'll just do one last session now, and then we'll go to the coffee break if that's okay with everybody. Any questions for Neil? I have one. Okay, so my question for you, Neil, in my experience in growing with Pythium, or challenges with Pythium, is oftentimes I've found that Pythium is prevalent in certain cultivars, cilantro, for example. I'm wondering, is that an environmental issue, or could it be endemic in the seed itself, or is it an issue that I'm missing?
Yeah, so Pythium is a very common problem in several of our hydroponic leafy greens and herbs. I see hydroponic spinach and basil as being maybe the most sensitive. Cilantro and arugula or rocket are also very sensitive to this Pythium. And then lettuce and kale seem to be decently more tolerant. I think it's typically not because it was carried with the seed, but just that the crop is inherently more sensitive to Pythium. So it's very easy for Pythium to spread, and then in a hydroponic situation, we have zoospores that can infect the plant. So we can control the environment to help control Pythium if we make sure, like, for example, the species of Pythium that we see under warm temperatures, Pythium aphanodermatum, if we can cool the root zone, so use a water chiller and cool the root zone to, say, 20 degrees Celsius instead of 24 or higher, we can really slow down the development of that disorder. But following all of our greenhouse, like sanitation practices are important for Pythium. Okay.
Check. Is this mic off, gentlemen? Okay. Oh, I'm back? Here, we're back.
got it.
Okay, a couple more questions here, Neil. How to manage, is that BAMO virus in a hydroponic greenhouse? Am I reading that?
Oh, tobacco mosaic virus?
Thank you very much.
Yeah. We'll have some pathologists, I think. Let's have that be a more pathological discussion. That can be sometimes a plant or a seed transmitted And also insect control is important, so some insects can transmit that virus. And in terms of tobacco mosaic virus, actually like smoking, cigarettes can carry the virus. So after our cigar smoking tomorrow night,
we'll go to a farm.
We'll not go to a farm.
Okay, got it. One more question, guys. How about carbon? What does carbon deficiency look like? And when would you impose CO2 as a supplement?
So carbon deficiencies, so I was talking about mineral elements. The plant is getting carbon from the air, which we could save that for a different discussion. But this would relate to the photosynthesis of the plant, right? And so if we have conditions where we're giving good light to the plant, but carbon dioxide is getting low, such as if you have a very sealed growth room or a very sealed greenhouse with inadequate ventilation, then carbon dioxide as a substrate for photosynthesis will not be adequate. And then as was discussed earlier this morning, maybe you want to really push the plant under high light. The plant can't photosynthesize most efficiently when you have high light if you only have ambient CO2. So if CO2 is only 400 parts per million, the plant can't fully utilize all of the energy from light that it's getting because carbon dioxide as a substrate for photosynthesis is insufficient.
Can we give Dr. Masson a nice warm welcome? Thank you, or nice hand. Thank you. Okay, I don't know if you all know this, but you're on television right now. I have been asked to make an announcement about streaming. So we're streaming this for the next few days. It'll be on Facebook and YouTube. For those of you that are Facebookers, it is essentially ICCEA LATAM, International Congress on Controlled Environment Agriculture. And I'll say this again tomorrow. And on YouTube, it's ICCEA 2019 _ ICCEA 2019 _ y los streaming quedarán grabados para cuando quiere verlos. Okay, it'll be there when you want to see it. All right, let's move on and make this fast. Thank you very much again for your attention. You guys have been wonderful. I want to introduce somebody else who is a doctor. And by the way, when you look at your program and you just see their name, it's just a misprint. They're all doctors. That's Dr. Hernandez, Dr. Vestra. They're all doctors, so we know that, and we're happy to have them. And by the way, if you thought Dr. Marcellus' energy was high, this guy has got great energy, so please be prepared. Assistant professor in the Department of Horticultural Sciences in the area of horticulture energy at North Carolina State University. Dr. Hernandez holds Bachelor's of Science in Agronomy, crop consulting from New Mexico State University. He also has a Master's of Science in Entomology, biological control from Texas A&M University, and a doctoral in plant sciences, plant physiology from the University of Arizona, and a doctoral minor in entrepreneurship from the McGuire Center for Entrepreneurship, Eller School of Business, and a minor in agriculture and biosystems engineering from the University of Arizona. Please help me welcome Dr. Ricardo Hernandez.
Okay, la última y nos vamos, right? So this is the last talk. I just want to say en español, para que escriban sus preguntas en español, yo las leo en español y las contesto en español, okay? Para que me hagan preguntas. So my Spanish is better than my English, but I'm going to present in English because this is an international conference, okay? So today, I'm going to talk about the power of changing colors. But before we talk about that, I want to talk about my vision of the production of lettuce and leafy greens in vertical farms, okay? So I typically divide this production into sectors. This is the United States, and the size of the lettuce actually represents the amount of production done in that state of lettuce compared to the total production, right? So you can see the biggest heads are in California and Arizona. So they produce around 96 to 98% of all the lettuce, field lettuce consumed in the United States. So they ship everywhere in the United States. You can see some little heads here and there, like Florida, Colorado, and some over there in North Carolina. And those are typically produced in season and sometimes in controlled environments. So you can see from this example that it's obvious that the lettuce production is centralized in 2 states. So I divide the market for vertical farm lettuce or controlled environment lettuce into 2 different sections. One is the direct market competition. What I mean with direct market competition is that if we want to compete with that field-produced lettuce, we need to be very efficient and create a lot of biomass with very little resources, right? So if I was a vertical farmer, I will ask myself, I keep looking here, as a vertical farmer, can I contribute by helping to decentralize the production and produce locally? Yes, you could, but you have to compete in pricing. And to compete in pricing, you have to focus on efficiency, both economically and environmentally. And there is companies and research programs focusing on that. However, there is challenges. Look at this video. I took this video in California, in one of those states. This is romaine lettuce. Okay, you can see the fields and fields of romaine lettuce. What I want you to focus in this video is in the amount of lettuce that is left behind. Okay, so here you have the harvesting crew, and they're taking the lettuce and cutting some leaves off and packing it and then sending it to your favorite store, all the way to North Carolina, all the way to New York, right? I want you to focus on that, okay? And focus on that gentleman with the hat, okay? So focus on that next head, okay? Look at that, boom. Can you replay that again, that last part? Look at that. Look at that. Boom. Boom. Okay, no, not so fast, but boom, okay? So 40% of the biomass produced stays in the field. It just stays there. It rots and gets incorporated into the soil, right? So we're here trying to be more efficient in a vertical farm, while this system can be a lot more efficient. So it's a challenge, right? It's a challenge to compete with this, right? Then the other market that I typically think about when I think lettuce and vertical farm is the niche market, right? Can I, as a vertical farm grower, create a lettuce product that is not currently offering the market, right? Can I create a product that, since it's niche, I can get better margins for it, right? Can I guarantee an amount of antioxidants, right? Can I guarantee good taste? Can I guarantee perfect texture or good color? If I'm able to guarantee that, maybe I can get a little more for it. I like to use an analogy for that. It's buying the Apple Macintosh computer, right? This computer over here does the same thing than a PC computer, right? You do exactly the same thing, but because this computer looks nicer, this computer is lighter, this computer probably gets less viruses, it has the cool factor. And a lot of people pay a lot for that cool factor, including me. I have a Mac myself, right? And I'm a little ashamed of it, but I keep buying it, right? But so that's, to me, is the niche. Can I create the Macintosh of lettuce, right? That also has challenges, okay? This is a graph that on the x-axis you have different countries in the world, and on the y-axis you have the percent of the budget spent for food at home, okay? Have different countries here. You know, coming here from the U.S., you can see the U.S. only spends 7% of the household income on food. So we like cheap food, right? We don't like to. If we get an extra $100, we don't go and buy more meat. We go and buy a pair of sneakers, right? We don't like to spend a lot on food. So it's a challenge when you're trying to create a niche product and asking for us, the consumer, to pay more for food. Or it's an opportunity, right? So there is a lot of disposable income. Can I now spend more on food? But there is a completely cultural mindset that is actually happening now in developed countries, right? It's like the beer. In the past, I only drink Corona, Bud Light, I don't know, the Panama beer, right? Now, I want the specialty, microbrew, IPAs, right? So I'm willing to spend a little more for those specialty beers. So I think for a vertical farm to be successful, it has to focus. It's a delay here, but I'm going to wait for 1 second to see if it seems like it's safe now to go forward. Okay. I think for a vertical farm to be successful, it has to focus on both. Try to be competitive on pricing, and at the same time, create something a little unique, right? So at my laboratory at NC State University, we're trying to work on both. We're trying to do some molecular breeding to actually create some cultivars that will generate more biomass with less in indoor environments. And we're also manipulating the spectrum to actually change the colors and try to get more with less. And today, I'm going to share with you our efforts on dynamic light recipes. So, quick introduction. This is daily light integral. You know, this is how you can quantify plant growth, right? You can quantify biomass growth per mole of light. The total amount of light received in 1 day, you can directly correlate that linearly to the amount of yield. It's like a rain gauge, a pluviometer, right? The rain gauge tells you how many inches, how many milliliters of water you get per acre that day. It's the same with light. How many photons of light you get per 1 meter square of area per a day. If you know that number, you can directly correlate that to yield. Okay? So with this, you know that light is king. You know, plant is king for John, light is king for me, right? So light is king. More light, more growth. Now this is more about light spectrum. This is a generalized scan of the sun spectrum. And you can see the different colors, UV, blue, green, red, far red. And this is an oversimplified, you know, version of the influence of different colors on plant growth, right? So you have the, between UV and blue, you have reduced stem extension. You can also have lower leaf area. You can also have more anthocyanin concentration developing the plant. And then you have between 400 and 700 is mainly used for photosynthesis. Something that is not depicted here is that the ratios between the 400 and 700 also input plant morphology. And also you have the far red light. We heard Dr. Marcellis talking about that. They also help in photomorphogenesis. Can we stretch the plant? Can we make the leaves wider, right? And they also have negative effects. They may reduce phytochemical content as well. Overgeneralized. However, since now we have the control of the spectrum through LEDs, why don't we take this knowledge and actually try to change the colors to match the different plant crop stages? There is two main areas for dynamic spectrum. The first one is changing the colors of the light during the day, during your photoperiod, right? 24-hour cycle. I'm going to put out this color the first 3 hours, this color the next 5 hours, right? That's one way. Another way that we do in my lab, we actually take the plant growth stage and we change it through that plant growth stage. So multiple days, and they change the color another few days of that. Okay? So there is some research done in this dynamic light spectrum, and most of it is actually on changing the colors through the day, right? Let me give you an example for some colleagues in Japan. So this is changing the colors through the day. I'm going to spend some time on this. So here we have the hours, right? 0 to 24 hours. This is the photoperiod when the lights are on, 0 to 14 hours. And then this is the color of the light during those hours. Okay? So here you can see that for this treatment, the plants had around half of the light blue and around the other half red at the same time. So 50-50, right? In this treatment, they actually have a few minutes only blue, then they have both of them on, then they have a few minutes only red. Okay? Then you have this treatment. They have a few hours only blue, then blue and red, and then a few hours of red at the end. And then you have a last treatment. a little bit more hours of blue, and then both, and then a little more hours of red at the end. Changing the spectrum through the day. And they found with that light recipe, here you have your fresh mass, which typically is what you're selling in lettuce. In the bottom graph, you have your leaf area, which is typically what you sell on lettuce. And you can see the difference, right? So these two dynamic spectral recipes actually increase the fresh mass and the leaf area compared to the other treatments, using exactly the same amount of energy, right? Only one limitation in this study is that they only group plants to this size, right? So they're considered, leafy green size. And also, for leafy green size, you don't have that density, right? If you were a commercial farm, you will have those, if you harvest at that stage, the plants will be very close to each other, right? So I think if this study can be done again at a higher density, I would like to see those results. But there is potential, right? Now what we do, and what I'm going to present to you today, is the change of color through the plant growth stage. This is a typical plant growth curve, the sigmoidal curve trajectory, right? So first, when you plant this little seedling, the first few days is an exponential growth. So why don't we give light color for that exponential growth? After, you go into the linear growth. Why don't we give another color for that linear growth? And at the end, you go into the to the growth that is kind of flattened, right? And why don't we give another color during that growth? So this is the premise of this research. Can we increase the plant growth by matching the color to the plant growth stage? But how do we do it? Which color? When? When do I turn it on? When do I turn it off? Right? There's 100 million combinations, right? So in our lab, in order to find the answer to that question, we actually did a preliminary study, right? And what we did, we grew plants under different color spectrums that were fixed. We didn't change them. Just same color to the entire growth stage. And then we harvest plants very often, every week, every 2 weeks, every 3 weeks, and we track the growth of these plants to try to find out at what point the plant is better in a different spectrum. Right? So here we have 100% red, 20 blue, 50 blue, 80 blue, 100 blue, fluorescent control, and we even try a sun ratio in there, mimic the sun indoors. This is a scan that we took from the sun outdoors. And we found this is a transplant stage, right? Same conditions, same temperature, same everything, but different colors. We found here that the drawback of some of the treatments was that, for the 100% red, even though they have good fresh mass, they had the red light syndrome, right? The leaves were curling inwards, right? So we don't want that, right? We want the leaves to be expanded, right? And the blue one, you can see 100% blue, they were stretching, and they were stretching so much they couldn't stand by themselves, right? So we don't want that either, right? So those are drawbacks. So we found that for that specific amount of time, around 17 days, lettuce under the recipe of 2080 had the most dry mass, 18% more than any other treatments. So we said we're going to use that for that phase, which is part of still of the exponential phase, right? And like I said, the 100% red had good fresh mass and good leaf area, but the leaves were curled. So we didn't pick that, right? So those two are good, but we picked the 2080. Now when we actually grew the plant to the final stage and the very, very high densities, probably too high, we found that the 100% blue actually had the most leaf area and also the most fresh mass, right? And also between 20 blue to 80 blue had the most anthocyanin concentration, 3 times more than the 100% blue. So we think, well, those are good characteristics of those plants, right? Now, A disadvantage of a dropback is that, for example, the sun, even though it had good leaf area, it had bolting. We actually pushed that plant to flower. And we were growing these guys under a 20 degrees Celsius temperature. Very cold. Those lettuce shouldn't bolt. So we push it to bolt. Then we took that fun and do something else with it, but it's not good for production. We don't want it bolting, right? So we use that spectrum, right? So we want for transplant stage a good combination of red and blue. And then we want for that linear stage more leaf expansion, but still create some growth. So we did 100% blue. It's still within the photosynthetic range, but now extend the leaves. You know? And then we wanted to, on that stagnant phase, the last when the growth is actually flattened, we wanted to take advantage of that time to actually come in color, right? Give more nutrition, get more anthocyanins during that plant. So we use a high blue, 50 blue, 50 red, right? So this was our first try for iDynamic, right? We did other things too that I'm not going to go into because it gets kind of complicated. But we also have a couple of treatments with end-of-day far red light. You saw Leo present about the benefits of far red light through the photoperiod. This end-of-day far red light is actually only given 5 micromoles of light, which is very, very low amount, for 30 minutes before you turn the lights off. Right? So end-of-day far red light. And there is some research done where that actually increases leaf expansion, and you need very little energy to achieve that. Right? So we have a couple of treatments like that, but I'm not going to focus a lot on them because the results are not as exciting as the other ones. But just be aware if you see more pictures. So we created these recipes, and then we harvest around the 17th day. We took measurements, around 25 days. We took measurements again around 32 days, and we took measurements again around 40 days, and we took measurements again around 47 days to track that growth, and see what happens. So this is harvest 1. Actually, harvest 2. Harvest 1, they were all grown at the same recipe, so they were all at the same stage. So harvest 2, we'll call it harvest 1. This is how the lettuce look. You can start seeing some differences. Right? I want you to focus on the fixed spectrum and on dynamic spectrum the most, this one and this one. You can keep in mind the other ones too. So here you see fresh mass. Actually my fixed spectrum is doing very good. It actually has more fresh mass than my dynamic, well, around the same than my dynamic, actually more than my dynamic and end-of-day far red, right? Leaf area, they're all doing good, right? We see some leaves that are actually extending more, but probably those plants have less number of leaves, so overall the total leaf area is the same. Okay, nothing's happening yet, but obviously plants are looking differently. And then dry mass. Dry mass, even though you may not use lettuce for calorie intake, dry mass is the definition of actual growth. Is the plant growing more or not? Oh, wow, my fix is doing better, right? So my dynamic thing is not really working, right? So we have more dry mass on my fixed spectrum versus my dynamic spectrum, okay? Good. So let's see what happens on the next harvest, okay? Clearly the lettuce keep looking different and different, all right? So we have, again, fresh mass. My fix is better, right? Leaf area, no difference yet, right? More layers in one on top of each other while other ones are stretching more and changing their angles. You can see from the bottom picture now that the leaves on the dynamic start doing this. They want to fly, right? And the leaves on the fix, they're typically like normal leaves doing this, right? But still, we can see here that my fix has more dry mass at this stage, right? So if you're going to harvest at this stage, it's probably use fix, right? The picture looks big, but those lettuce are quite small still. Okay, harvest 3, right? So now we can see that we have fresh mass, leaf area, the same again, and dry mass. Now at this point, this is red lettuce, so they all should be red. You can still see the dynamics are actually more greenish, but they have to be red. So at this point, we took these lettuce and put them under a coloring spectrum, 50 blue, 50 red, to start coloring them more, okay? So just keep in mind these results, okay? We're taking this lettuce, putting them in a coloring spectrum. So this is what happened during those days. right? So this is 7 days of treatment. You know, this light quality still drives growth, so the plant keeps growing and at the same time it's coloring. You can see the ones on day 0 before treatment, you know, already pretty purple, and then they got maybe a little more. And you can see a clear difference in the bottom, where they're more greenish and they got more red. So let's break it down. I took some days out, right? So this is day 1. So they've been under this stream for 1 day. You can see the bottom lettuce looks pretty green. Day 2, you can see it's coloring, right? Day 5, you can see you have a little more color, right? And day 7, you know, is clearly different than day 1. Right? And you can see that again here. So you have the top, which is day 0 before the coloration treatment, and day 7. And you have the bottom, day 0 and day 7. Clearly difference. Not only difference in coloration. Look at that now, at the dynamic. To me, it looks much bigger. Right? So this is anthocyanin. This is what happened with anthocyanin. In this graph, you have the fixed spectrum, which actually, and on the white bar, you have day 0 of treatment, right, before it went to coloration. And then on the gray bar, you have after treatment. You can see an increase. It was not significant. We probably need a little, almost there. There was a little high increase, but not by much. Not significant. You can see the dynamic, you know, with a little star on top. Oh, that little star on top that is actually significant. So we increase the color, and it's obvious by look. Okay? Now, these letters actually compare the two lettuces, the one in the fix and the one in the coloration. So probably I needed a little bit more days to have it at the same. But statistically speaking, they're the same. They're both, you know, the same amount of anthocyanin. So we accomplished that. We colored that. Okay? Now look at this. This is what happened. Right? Okay, so that's the canopy diameter of this plant. Okay? Right? If we translate that, that's the canopy diameter of that plant. Okay? So that's the canopy diameter of the dynamic plant. Okay? If you translate that, and this is to scale, you know, that's the canopy diameter. Right? So it's actually 25% bigger canopy diameter. Now, fresh mass is the same. They weigh the same. Number of leaves, they have the same number of leaves. But the canopy looks much bigger. Right? If you're selling lettuce by weight, no difference. If you're getting your lettuce put in a clamshell, you're going to fill that clamshell much faster with the dynamic. Okay? Not only that, we also had an increase of 13% on dry mass, right, with the dynamic. And that only happened during the coloration stage, during those 7 days. Before going into the 7 days, you know, the fix was better. After the 7 days, the dynamic came ahead, right? And so we're very surprised about this finding, right? So let's discuss this a little bit, okay? So you have the 100% blue actually created a different plant architecture, right? So when we inspect, and at the time we didn't know how to quantify these, but we inspect these plants, we start seeing that the leaves on the dynamic actually started doing this, right? They started going up. And we've seen this in cucumber when we grow them under 100% blue. Right? Instead of going down, they actually stay up in parallel. We see that in pepper seedlings also. Right? So we're seeing the same with lettuce. And actually here, you can see, maybe not very well, but you can see how these leaves are droopy and these leaves are actually going up. Right? So the angle of the leaves is changing, and that's giving that new look of being bigger. But not only that, you know, you have these plants growing at very high density, you know, where leaf expansion is best to capture light until there is no more space for them. Then leaf expansion is actually maybe counterproductive because you don't need to expand anymore. All the area has been taken, right? But what if, this is our hypothesis now, we haven't tested this, but what if the leaves actually started opening up like this, right? And they allow more light penetration to the deeper canopy. So I think that's what probably happened here. and where that angle actually allows for the plants to start taking more photosynthetic rate. Also, at the same time, we changed it to a light quality that has a higher photosynthetic rate, and then we ended up with more fresh, more dry mass. Also, you know, our 50-50, it was good to create that coloration, especially in a dynamic that was actually missing coloration, right? So that's what we found indoors. And I got all excited. And I told my student, let's try this in the greenhouse. Now, what if we can do that same in the greenhouse? Now, remember, in the greenhouse, you have the sun. And the sun has a very well-balanced spectrum, right? And, you know, in long days, or most days, you have a lot of that spectrum. So your limitation on changing the spectrum, you're more limited on changing the spectrum because all the colors are there already. But we tried it anyways, right? So we grew some lettuce in the sun, and then we harvested multiple stages. And today I'm just going to show you 2 of these stages, you know, the transplant stage and the final plant growth stage, right? And we grow in the greenhouse, we keep setting the light, and we change, you know, we only change the color to the dark hours, right? So we did a previous study before this where we're growing lettuce under 24 hours in the greenhouse. You know, we decided not negative impact in growth, so we decided to keep this at 24 hours, so we have more dark hours where we can play with the spectrum. So actually, when you had the sun, we give LEDs all the same, a lot more light. When the sun set, we change the colors during the night, after sunset, and change the colors, you know, before sunrise. You know, with this blue, you know, blue try to get those leaves off, and then you have your common blue and red, which is just red and blue, and then you have your standard, which added some white light also. And the results were marginal. See here you can see the transplant stage. You can see that same behavior, right? Where these are 2 different cultivars, Cherokee and Red Cell. By the way, Red Cell produces a lot more biomass than Cherokee, right? And they're both red lettuces, so if you're looking for a good plant to grow indoors, Red Cell is a very good plant to grow in controlled environments. But, you know, between the treatments, no difference in Cherokee. So basically, your light treatment didn't do anything. More light, more growth. And on Red Cell, actually, your blue started creating more leaf area, right? But this is just transplant stage, right? So if you're producing lettuce for transplant to go in the field, this information may be useful. But if you're going to produce the full plant in the greenhouse, probably not, right? And by the final harvest, you know, we actually seen that difference disappear, right? So the colors of the sun, you know, are actually meeting a lot of, they're governing the morphology of the plant more than those colors that we added at different points. So my advice from this specific research is that in the greenhouse, just give them more light, right? You can increase the amount of light as long as you're keeping below the 17 moles. If you can increase the amount of light during those dark hours just to have more photons there, you're probably going to have the best than trying to change the spectrums to maybe wavelengths that are not as photosynthetically active. So this is how the plant looked at the end. You know, Red Cell, much bigger plant, you know, and, you know, they practically look the same, right? So to conclude, we know dynamic light recipes can help increase the production efficiencies in vertical farm systems. You know, we also show that a 100% blue can be used to change the morphology of the plant while still drive some of the photosynthesis, right? If you grow them in 100% blue all the time, the plant is not going to look good, right? But if you actually use this signal and photosynthetic capacity to change the morphology, you may yield a better plant. Also, we know that through coloration, we can use, and this was also shown in the greenhouse by a different group in Michigan State, right? So you can color these plants using high levels of blue photon flux. And the dynamic recipes, specifically this recipe, had a minimal impact on the plants grown in the greenhouse. Okay? So this is work was carried out by my student, my former student. He graduated, Dr. Hans Spohls now. He was my first student graduated from my lab, so very proud of that. And now he's a plant scientist at GE, working with them. And so all the credit goes to him. And also I want to thank my lab at the university. And I will open the floor for some questions. And thank you very much. Oh, I have another talk on Friday, the last talk, okay? So I know it's difficult to make the last talk, but it's about CO2. So thank you very much.
¿Alguna pregunta para Ricardo? Allí.
¿Pregunta? Gracias. Gracias. Ok, esta pregunta es bastante pesada y filosófica. ¿Es la hidroponía considerada una producción ecológica? Right? Is hydroponics considered an environmentally friendly practice? En mi opinión, es una herramienta más y todo depende del manejo, ¿verdad? Si hablamos del uso del agua, se usa menos agua que en agricultura abierta, ¿verdad? Si hablamos del uso de nutrientes, se usa menos nutrientes que la agricultura abierta. Ahora el manejo de residuo puede crear problemas, pero si se maneja correctamente, en mi opinión, es una herramienta más. No es para reemplazar la agricultura convencional, es otra herramienta. ¿Sí? My opinion on that is that hydroponic production is sustainable, and I think especially when you talk about the use of water and the use of nutrients. And I also think that it can create problems, especially if you don't manage your runoff, right? But I think in general it's another tool that we have to produce food, and that is not to replace the field production, but instead to complement the field production. ¿Cuáles son los costos por metro cuadrado oficiales de fincas verticales? Promedio de rentabilidad de la producción. Muy buena pregunta, esta es muy buena pregunta. Y los costos de construcción varían mucho, depende del sistema. Varían desde los más baratos que he visto yo es como $125 por pie cuadrado para construir. Ustedes ahí le hacen la matemática. Y pueden llegar hasta $500 por pie cuadrado, pero no estoy muy bien informado en esa área. La rentabilidad, mi único consejo ahí es de que depende de tu sistema y depende de tu producto. Esta pregunta me llega mucho ahí en mi oficina y la manera que yo contesto es de cuál es tu mercado y cuál es tu producto, ¿verdad? Y cuáles son los márgenes de ese producto, ¿verdad? No hay que empezar con el sistema, hay que empezar con el producto. Si para obtener estos márgenes necesitas usar agricultura controlada, entonces adelante. Pero si no se necesita, ¿verdad? No se necesita tener la mejor tecnología para producir algo simple, ¿verdad? Entonces depende del producto, es como se define el sistema. The question was what are the costs? Is it profitable to produce in vertical farms? And what are the costs of construction? My answer is that I don't know really the cost of constructions. With some interactions with some companies, I know they can range from 150 per square feet, only no shell, right? So only the retrofitting of a building to even 500 per square feet, but I don't know. I'm not versed on that area. And then the second question was, can we make any money doing this? And I said, you need to start with your end product. You offer a product. Don't start with the system. You know, if you need a product and you have healthy margins and you require a controlled environment system to produce this product, go ahead, right? But if you don't, then don't, right? So it depends on the market and the product. ¿Alguna otra pregunta? Any other question? Gracias. ¿Cuál es la distancia sugerida entre la planta y la fuente de luz artificial? La distancia comercial es como 25 plantas a 32 plantas por metro cuadrado, ¿verdad? Si uno quiere crecer la cabeza entera o una planta más grande, ya depende de cuándo se cosecha, ¿verdad? Si uno nomás está haciendo germinados o verdolaja, ¿verdad? Pequeña, entonces la densidad puede aumentar. And la fuente de luz artificial, la cantidad de luz necesaria, típicamente para trasplantes y también para lechugas, como entre 12 a 17 moles por metro cuadrado por día es recomendado, ¿verdad? Eso es lo sugerido para cuando uno crece dentro de CO2 a nivel ambiente. The question is, what is the plant density and also what will be the light intensity? I said the density ranges between 25 to 32 plants per meter square when you grow in the full head. And also a good DLI, daylight integral, will be between 12 and 17 moles per meter square per day. And that's when it's grown under ambient CO2.
Ok, muchas gracias. Queremos darle gracias a Ricardo por estar aquí con nosotros, igual como todos los oradores que estuvieron hablando hoy, el día de hoy. Muchas gracias por parte de todo por estar aquí compartiendo su conocimiento. Un aplauso. Muy bien, Ricardo. Muchas gracias. Ok, muy bien rápido. Yo sé que ya están cansados, se quieren ir. Y hay coffee break ahora. Por favor, no se vaya sin comer toda la comida que hay allá afuera. Entonces, bien rápido, para un tema de... Jim se tuvo que ir. Y la razón que estoy aquí porque tuvo un problema y él está ahora en el dentista, sufriendo porque tiene que hablar una muela o algo. So, él regresa mañana si puede hablar. Pero bien rápido, para mañana tenemos el doctor Escudero que va a hablar un tema importante para Panamá, que es el CIPAC, Centro de Investigación y Producción en Ambiente Controlado. Todo esto que estamos hablando aquí en estos 3 días se va a desarrollar un centro de clase mundial en Panamá para que todos aquí podemos entonces tener toda esta información día a día para ayudar nosotros en lo que es la producción de ambiente controlado para invernadero o la finca vertical. I'm going to say this in Spanish. I think the majority of the people, if you don't mind, I'm just going over pretty much what's going on tomorrow from the list. Entonces tenemos Pablo López, que es la innovación del sector agroalimentario utilizando el blockchain, una nueva tecnología de la industria industrial 4.0 muy interesante que está revolucionando el sector agrícola. También Fabián Chierre, el food chain, que es cómo se puede solucionar los temas que tienen los productores, comercialización, eliminar los intermediarios, obtener crédito y financiamiento para la producción agrícola, pago más rápido, seguro, en sí resolver problemas que tiene el productor. Entonces tenemos al doctor Kevin Ford de la Universidad de la Florida, reproducción de semillas diseñadas específicamente para la finca vertical y invernadero. Están desarrollando semillas específicamente para tener alto rendimiento y de mejor calidad. Entonces tenemos el David Schwarzman, consultor agrícola de Israel, donde el método de irrigación hidropónico, el doctor Murat García de la Universidad de Arizona, donde va a hablar sobre el control y manejo del clima en los invernaderos y la finca vertical. Joanna Hebner del PMA, muchos lo conocen, que han visitado el Produce Marketing Association. Esta es una charla muy interesante donde va a hablar de la tecnología agrícola, la oportunidad de retos y tendencias de aplicar tecnología en la finca. Tenemos entonces el doctor Hugh Poole, consultor internacional de la agricultura, produciendo con éxito es una serie de decisiones. Como todo en la vida, si tomamos buenas decisiones, vamos a tener éxito en lo que estamos haciendo. Tenemos entonces, en lo que son los breakout sessions en español, tenemos bien rápido al ingeniero Rolando Armuelles del MIDA, donde va a hablar de los agroparques. Muy importante esa charla para los que está interesado. El gobierno está promoviendo, creo que son 7 agroparques de 200 hectáreas cada uno, y creo que hay 1 o 2, son 1000. Una charla muy importante. Pablo Cedeño, director de Iberoamérica y Caribe de MSC Fábricas Agrícolas, que tiene un stand aquí. Novedades en los tipos de plástico de invernadero en climas tropicales. Aquí ha habido mucho problema con los invernaderos porque no están climatizados. Él va a hablar sobre este tema. No puede invertir en un invernadero si no sabe que, o sea, lo que funciona en otros países no necesariamente va a funcionar en Panamá. Tiene que diseñarse específicamente para el clima que tenemos aquí y va a hablar sobre esa charla. Lo otro es ingeniero Miguel Murgas Río, Dirección Agrícola de MIDA, experiencia de la agricultura protegida en tierras altas y provincias. Y ese sería para mañana. No se lo pierda, lo esperamos todos. Y como dije, tema muy importante mañana. Y conozca a los speakers. Ellos están aquí, quiere conocer, quiere ayudarlo en todo. No tengan pena. Preséntese y hable de su proyecto y tema. Y créeme que ellos van a poder ayudar, igual como la fundación, que estamos aquí precisamente para eso. Muchas gracias. Tenemos el coffee break y lo vemos mañana a las 8, ¿verdad? 8. Bueno, hasta luego.
Jump into the fire. I'd like to see your wild side. We should run away. But the sun never goes down. Time has slowed down. Would it be too crazy if we decided to stay?
mistake. Lost touch, but I think I've been replaced. Evidently, something's gotta give. Played safe, but I know you're worth the risk. You built this fortress. I stumble towards it. I stumble towards it. And guilty I may be, but don't give up on me. In the wake of the Odyssey, we will still be big as thieves. You and me still big as thieves. I got an escape if you want it. We can leave first thing in the morning. We'll be back before you know it. We're as big as thieves. And guilty I may be, but don't give up on me. In the wake of the Odyssey, we will still be big as thieves. And guilty I may be, but don't give up on me. Don't you give up in the wake of Evidently, we can't work it out. I guess that courage ain't allowed. Evidently, you're not in the mood. And everything I say just bothers you. You built this fortress. I stumble towards it. Evidently, you look furious. Walls up, and I know you're serious. Evidently, I'm not always there. You left and I looked everywhere. You built this fortress. I stumbled towards it. I stumbled towards it. And guilty I may be, but don't give up on me. In the wake of the Odyssey, we will still be big as thieves. You and me still big as thieves. Evidently, this is my mistake. Lost touch, but I think I've been replaced. Evidently, something's gotta give. Played safe, but I know you're worth the risk. You built this fortress. I stumbled towards it. I stumbled towards it. And guilty I may be, but don't give up on me. In the wake of the Odyssey, we will still be big as thieves. You and me still big as thieves. I got an escape if you want it. We can leave first thing in the morning. evidently